Sorry, we're going to wait. Wants to wait just a couple more minutes. Unfortunately, with your 38 to 37 minutes, down to 5 minutes. Okay. What would you if you had a choice, would you rather wait until more people show up, or would you rather go ahead?
I'm not sure.
I know what you mean, yeah,
Of course, it's nice to have time for discussions afterwards.
I know, that's the thing, we're going to lose out at the end.
Yeah.
Because we sort of have to stick to it. Here's 2 more. Okay. I think probably we'll be in a situation where some other people probably keep coming in for a few more minutes, but if we don't start now, we're going to lose discussion time at the end, and I don't want to lose that. So I just first speaker this morning, and then the invited speaker is Dunda from Equinor, and it's going to be about something about sparse precision matrices and a new type of filter that can use that. So, go ahead.
Thank you for the introduction, and thank you to the organizer, especially perhaps Xiaodong, which has been running around and helping with everything and still finding time to ask good questions. We have a title here called the Graphical Sparse Precision Matrix Estimation and the Ensemble Information Filter, and it's by I'm presenting, but I have 2 co-workers there that are named Feja and Sundre as well.
You have to use the mouse the first time.
Okay. Let's see if it works after this. So we are the scientific computing team in Equinor, abbreviated SCOUT. And this is what we do from day to day. We really care about software and kind of coming in a little bit from the side to this talk. But hopefully we can contribute something. Yes, now it works. So you cannot see it, but it is divided into 4. The talk is divided into 4 sections. The first is the background, where I will motivate our new filter approach, which is the 3rd section and called the Ensemble Information Filter. However, there is a key that you need to unlock, and that's the graphical sparse precision matrix estimation. The 4th section is just examples. When I have timed this, it has been around like 40 minutes. So there are a few slides that I'm going to skip so that we are certain that we have time. And when we come to those slides, I will just say what is the main importance from them and go to the next one. So background. Typically, we have a stochastic partial differential equation exemplified here with the heat equation, the stochastic heat equation, right? And you can see some simulations from it here. So we have a model, and then maybe we have some sensor measurement point, let's say exactly in the middle here. And we want to assimilate this into our belief about the world. The ensemble Kalman filter approach is to have a Gaussian field prior at time t-1. The sensor point is at time t. Then take each realization, bring it forward in time to time t. And here you see the average field, the prior mean field that you would have, which is kind of the best estimate from the prior. And then we would use the Kalman filter equations to update to the posterior. And here you see the posterior mean field. However, all is not well with this approach, as I think most are aware. Here you see the update, so the difference between the mean prior and posterior. And you can see that in the middle, where we did have the sensor point, you have a stronger update than the other places. But if we look, inspect this some more, we see that indeed here the field is vectorized, and you can see that there is a lot of randomness propagating into this posterior. And this is because of this is a 100 by 100 field, meaning that the covariance is 10,000 by 10,000. It's quite hard to estimate in a proper way, especially using 100 realizations. So here I cannot even plot it, but here is 5% of the covariance matrix, and it's very dense and lots of spurious correlations. Of course, we have solutions somewhat for this, and this is called localization, and I'm very glad to see that it seems to be a hot topic because many presentations have indeed employed localization. In the approach here, you have some variance to it, but in the approach here, you have a tapering function which you choose, and then you can use this to somehow dampen the update to the posterior. And here we have done exactly that. Then you get a more local update. The spurious correlations doesn't mean that the randomness propagates. And you can see the element update there. However, the localization approaches is very ad hoc. There is not a strong theoretical foundations to do this. It involves hyperparameter tuning, which I don't like. You have to select the functional form of the tapering function, and then you have to select some radius of influence, I think it is called. And we don't like this. Sometimes you have to do it, but it would be nice if there is another approach. So we started looking for another approach. And I myself is a computational statistician by training. And when I have a problem, I often look for a reparameterization of the problem that can help me. So to give some examples of reparameterizations, if you are doing maximum likelihood estimation for a probability, you are not going to optimize directly for the probability. You're going to use the logit transform, and then you have an unconstrained optimization problem. There was another interesting talk that took an unconstrained optimization problem and transformed it into a constrained one, but that was for theoretical purposes. It's not something usually you want to go the other way around when you have numerics.
You can do maximum likelihood for a probability. That sounds like a circular kind of thing where you just go to.
This is the Bayesian talking. So, but we can do so. Just if you have.
No, it just sounded great.
Yeah, it's just to set up the likelihood and then optimize. But similarly, in a GLM setting, but for another purpose, let's say that we have some probability. So again, we have the same likelihood function, and we want to perhaps create a confidence interval, confidence estimates or something around our best estimate from the GLM model. Then if you use a second order Taylor approximation, it's going to be not a very, very good fit in this untransformed space. But what you usually do is, of course, you use the link function of the GLM, which in this case is the logit transform. And here you can do a second order approximation, and then, of course, arriving at the Gaussian approximation. And then you can transform this back, and then you have a much better fit to the original function, giving you better approximations. My most favorite reparameterization is perhaps the state of the art of MCMC, where you have Riemann manifold Hamiltonian Monte Carlo. Hamiltonian Monte Carlo is very nice when you have something like on the right side, when the typical set of the distribution is round and nice. You have constant information in it. Riemann manifold Hamiltonian Monte Carlo is all about finding the curvature of the space at some point, which it turns out to be the Fisher information, and then use this to figure out how far you should go your step size in the Hamiltonian Monte Carlo, in the original one. What you can do instead of having to do, so then it became a big issue, like how do you find the estimate the Fisher information? But what you can do instead is dynamically rescale this problem so that you arrive at something that looks almost Gaussian, and it's called like a dynamical constant information parameterization, and then you can use HMC as you normally would on this problem. So reparameterizations are sometimes really, really nice for your problem. All of this, the point of this is to mention that reparameterizations are sometimes quite clever things to do in practice. So back to our problem with localization. Reparameterization, what are we actually looking for in a reparameterization for such a problem? And the temporary answer is that this dependence is local. And when we are estimating the covariance matrix, it has no preference for local dependence. It doesn't know anything that this point is closer to this point than this point, and so on. And it would be really, really nice if we, before we estimate the dependence structure of the problem, if we could tell through the parameterization that things are local, right? So that is what we see. We seek a parameterization that has a preference for local connections and dependence. And of course, when I'm talking about local connections and dependence, we should formalize it properly. And then it's natural to start talking about graphs. And here you just, a graph is a set of vertices and edges. And important here is that you would also like to talk about the neighbors of the vertices. And an example here is that you have the vertices 1, 2, 3, and 4. And the neighbors to, for example, 1 would be 2, as you can see from here. And the neighbor of 2 would be all 1, 3, and 4, because you have a direct connection to these vertices. When we have a graph, we can start adding Markov properties with respect to a graph. And a Markov random field is a d-dimensional random variable with respect to a graph with vertices from 1 to the dimension d. And it has a Markov property if xi is conditionally independent on the non-neighbors of xi, given that you have the information of the neighbors. So in the example here, you would say that x1 is conditionally independent of x3 and x4, given that you have the direct connection in x2. And similarly, you will go through and create Markov properties for the others. And this would then give you a Markov random field. So Markov properties, I will go through this very fast. I have a couple of slides. I will go through them fast. But Markov properties is really nice because it keeps modeling at the local level. If you are doing generalized mixed models with random fields and so on, then you are very interested in the expectation here that indeed the expectation, the conditional expectation of some variable is only dependent on the neighbors. But it's even stronger than that because you actually have conditional independence here, which turns out to be quite important. For our case, we are working with Gaussian random fields. Then we add Markov properties to Gaussian random fields. We arrive to Gaussian Markov random fields. And here, I just have put up the straight definition. What you can see here is the normal PDF. But instead of using the covariance parameterization, I have used a lambda here, which is the inverse of the covariance. And it's called the precision matrix. And the really nice thing about this, when you have a Gaussian Markov random field and parameterized with the precision matrix, is that the elements of the precision matrix is exactly 0 when you have conditional independence. What does this mean if we think about it? It means that we have a parameterization for our problem that has built in the concept of locality before we estimate anything. And that's really nice. Here are the next slides. I'm going to go through very fast. They are about the properties of the multivariate normal in this parameterization in comparison to the moment parameterization. But essentially, it is that for inversion, which is important for the Kalman filter, you don't really want to work with the moment parameterization because you have to do inversion. It's really nice when you are working with marginal properties of the multivariate normal, but not conditional ones, which is what you do when you have an update. The precision matrix, on the other hand, is really nice. It's all additive. It's super nice. And we will see this again later on when we reformulate some things. Here, we have an example. For numerics, it's important for this to scale, is that the covariance matrix is dense, even though we have some graph with locality, but the precision matrix will tend to be sparse. As I mentioned, that was the really nice thing about the precision matrix with this parameterization. So if we so this is done before, right? Using the precision matrix and reformulating the Kalman filter is just the Kalman filter, but we use the canonical parameterization of the multivariate normal. As you can see up there. The predict step is not that beautiful, but it turns out also that we don't really care about it in the end. So this is just the equivalent to the Kalman filter. And going to the ensemble ones, the predict step, we don't really need the equations for that, right? The update step is much nicer than in the Kalman filter. So there is no inversion, first of all, and it's all additive. It's really, really convenient. So let's just extend this to the ensemble information filter, right? What you would do then is, of course, sample from the multivariate normal. Then you would just use your forward model and integrate to the next time step. And then there are, of course, at least 2 ways to do this, but you can then estimate your parameters, let's say the mean and the precision with respect to some graph, giving you the Markov properties and locality of the field, and then you would use the update equations. But yeah, of course, the problem here is the red one, right? How do you estimate the precision matrix non-parametrically with respect to some graph, giving you the neighborhood structure? And this is a much, much harder problem than what we usually do with our covariance matrix. So the extension from and I think maybe that's why this has not been done before, the extension from the ensemble, the information filter, which is known for a long time, has not, at least in my experience, been done in a very similar way as the ensemble Kalman filter. It's quite hard to arrive to the ensemble information filter, which makes sense when you have a graph. If you don't have, it makes sense to do the Kalman filter. So for the background, I'll just go through it once more. For spatial temporal models, it's quite hard to do our traditional algorithms because of spurious correlations. And we seek to model at the local level, and that is why we arrive at the Markov properties. Amazingly, with these Markov properties that allows us to model at the local level, we can build it into our parameterization of the multivariate normal. And that is really nice for estimation, which I will go through next. Amazingly, again, the Kalman filter equations are just much easier in this parameterization, at least the update step, which we are interested in. There are some bonuses that you actually, if you start doing optimization to this, then you end up at the natural gradients for the problem, which is super nice for optimization. But our problem, how do we, so given that we have an ensemble, how do we estimate the precision matrix with respect to some neighborhood structure giving us Markov properties, so which is formalized in a graph? And that is the next section, graphical sparse precision matrix estimation. So the sample covariance matrix that we all know and sometimes love has some positive properties and some negative properties. So the positive properties is that it's just like a small scaling away from the maximum likelihood estimate if it exists, and it is properly formulated, which is actually, you know, more samples than dimensions and so on. But it's really nice for the Kalman filter because we actually don't have to work with covariance matrix. We can work with like the residuals of the ensemble and so on. And then we can do our updates in ensemble space, which is the numerical black magic that allows the ensemble Kalman filter to scale to very, very high dimensions. The negative properties is that it's unstable, this statistical estimate, and it's even singular when the ensemble size is smaller than the dimension, which it almost always is. In any case, it's inefficient. There are better estimates. And most importantly, it does not employ our information about locality. So if you have this graph in your mind, when you estimate the covariance matrix, you have no preferences. So there is it's a fully connected graph between everything, and there's no preference between any of the connections. And adding localization kind of gives us a preference afterwards, but that's only afterwards. So our first idea here, when we read the Holy Book of Evensen, was that we could work with the covariance matrix and add shrinkage to it, because we were aware of this Ledoit and Wolf paper that was also cited, referenced yesterday. It's a very good paper, but there you can arrive at the symmetric positive definite results using some shrinkage, typically of the off-diagonal elements of your estimate. Some comments here is that you have to select the lambda. So then we are back to hyperparameter tuning. To tune it, we need an objective that we then optimize, typically using cross-validation. And this is not that nice, but there has been some amazing work by some amazing people here in 2015, for example, is that if you use the Frobenius norm between the true covariance and your estimate, and then you use a sensible target matrix, and there are other variants of the target matrix, but then you can have asymptotic optimality results for the lambda here, and then you have no hyperparameter tuning. You have theory that gives you the hyperparameters, which is really nice. So this was our first idea, but if let's say that we are stuck at n equals 100 ensemble size, and then you start increasing the dimension, what happens with this type of shrinkage? What happens is that you will shrink all the off-diagonal elements, so the correlations, to 0 as the dimension increases. And the reason is that you don't know which correlations are more important or more local than others. I'm not going to go through the very smart approach. It's what they do. It's quite clever. So how to arrive to this lambda. It's so smart that it was recently applied with the ensemble Kalman filter, which of course we wanted to do, but it's good that others are doing the same thing as you, because it means you are on the right track. But as we also saw, and what we noticed was that this gave us better covariance estimates, which is important for the algorithm, but it didn't scale to very high dimensions because we were not able to build in the Markov properties and local modeling. So this is at the time when we realized this, then we started thinking about Markov properties and so on. So that's what we want to do. The precision matrix by itself holds the knowledge about the graph. So we want to estimate the precision matrix instead. Can we estimate it from data is the big point. And there are some things that you have to have in your head, because the covariance matrix is extremely easy to do, and the estimation scales to high dimensions. So our procedure has to be efficient and it has to scale well. There has been work on how to estimate the precision matrix. And here is like some of the important ones. But the most work has been to estimate the precision matrix, given that you know that there is some sparsity structure, but you don't explicitly state what the sparsity structure is. So the algorithms here are estimating also the graph for you. You're not providing it. And of course, we already know what the neighborhood structure in a field is. We know which points are close to one another. It's like if we have done a triangularization of them, we already have a graph, for example. Yes.
Where I go back maybe to the earlier idea, you don't have to change slides, just I was trying to remember why was it? So I would also expect if graph says that something is disconnected, that the covariance is zero, not just
so it's conditional independence, and if you have a conditional independence, then the information will propagate through the edges of the graph. So actually, maybe we can see. It was one of the slides I went through fast. So okay, maybe I should have not done this, but so here we have a graph, autoregressive one, and like there is no direct connection, right? The covariance matrix is dense, given by the autocovariance function, but the precision matrix is sparse. So, but still, these are equivalent. So even though we have a graph, which we always did with the autoregressive one, implicitly, and even though the precision metric is sparse, these formulations are theoretically equivalent. So the correlation does not go to zero. It kind of propagates. But that's the cool thing, right? So you're telling how the information should propagate through your system. But if you just work with the covariance, it's a direct connection. So where were we? Yes. So estimation of the precision matrix from data. There has been lots of work where you also estimate the graph. But we already know the graph. But the work on doing this has been sparse. But thankfully, very recently, like this paper from 2022, kind of came up with the procedure that we needed, and that scales very, very well. And we got lucky, to be honest, to find it. And it's I think it's titled non-parametric precision matrix estimation with respect to a known graphical structure. It's exactly what we need. But it's not. It has some pitfalls. It's not a symmetric positive definite estimate because it's a column by column estimator. So it's not necessarily symmetric because of that. And because what it essentially does is that it uses the knowledge of the graph to kind of take the sample covariance matrix estimate, like blocks of it, and then inverting it to the non-zero elements of the precision. That's kind of what it does. But these blocks can still be like non-invertible, right? So what we did was that we added this amazing theory for asymptotic shrinkage, right, that we saw earlier. We added these to all these blocks that are inverted, and then we have inversion, and then we have a symmetry conversion. So we built something that give you theoretical guarantees for symmetric positive definite precision matrix estimates with respect to a graph. And we have open sourced the repository, and we have also written a paper on archive quite efficiently. It's header only in C++ using eigen, and then we have bindings to Python and R. It's done from PyPy and on its way to Chrome. I will skip this, but in the paper there are 15 figures illustrating that it works very nicely. And it's kind of, you can see that when you increase the connectivity of the graph, then the asymptotic shrinkage effect of that starts giving you very nice estimates. But if you have a very known graph, then the asymptotic shrinkage is not that important because the block dimensions are not that big. But then the knowledge of the graph gives you very good estimates. So you have this, it kind of dominates the other procedures because it uses the best from different worlds. So a recapture of this section is that sample covariance matrix is easy to compute, but it's not necessarily what you want to do because it doesn't give you localization for free. Then you could use shrinkage, but it doesn't scale to high dimensions. Also, it doesn't have the knowledge of locality. So we created graph SPME that we can then employ, of course, in our assimilation algorithm to assimilate data. So that's what we do. In the next section, in the ensemble information filter, we have the exact same slide as before. Sample from the normal, predict step, and then we estimate the mean and the precision matrix using the graph SPME package. Of course, you can use the other algorithms. If you don't know the graph, but you know it's sparse, you could use one of the other algorithms, but we are using graph SPME with knowledge of the graph because we know the field. And then you use these amazingly additive update equations. So important, right? How does this scale? The ensemble Kalman filter and the covariance estimate there is kind of implicit, and it scales because you can do updates in ensemble space. We use a different type of numerical black magic. We use the sparsity of the problem. Because it's very sparse, the Cholesky decomposition is very efficient. We have some cases where we are going from the moment, not the moment parameterization, but the mean precision parameterization to the scaled mean and precision parameterization. And for example, right, so when we are sampling, we need the mean. But when we are updating, we are using the scaled mean. So we are going from this parameterization. Thankfully, it's a linear problem, and it's a sparse linear problem. So there are sparse solvers that we can use to do this, efficiently. And essentially, our black magic is the sparsity built into, for example, eigen and so on. And we have guarantees on SPD, which means that we can use the Cholesky decomposition. When you are using this in practice, you need to use it, you need to specify a sparse graph. So then you need to use a library that has sparsity in it. So in C++, you could use eigensparse, Python, sparse. In R, you could use the matrix package, which has sparse that combines with R. I will skip this slide, but it's a slide that says it works well. But this slide says the same thing, right? This is the problem that we had earlier with our field. So then we are using ensemble size 200, and here is the update using our theory. There is no spurious correlations that you can see, or at least it's very unproblematic. And the reason is, of course, that the number of parameters is not, now it's no longer quadratic in the dimension of the problem, but it's linear. On the right side, you have the ensemble Kalman filter, which still has the problem at ensemble size 200. What happens at ensemble size 10,000? Our algorithm becomes slightly smarter, but it doesn't change that much. It still works at 200. The ensemble Kalman filter still has problems. Well, of course, it's kind of okay, but still there is various correlations. So we have built graph SPME that allows the extension. It's the key that unlocks the ensemble information filter to go to an ensemble variant. We use sparse linear algebra to make it scale. And the filtering updates seem to be quite efficient because we are avoiding spurious correlations. So some examples. I really like the autoregressive processes because it allows you to select the connectivity in the graph. And it also, you can use the phi there to select and choose the dependence, like how strong should the different elements be connected. If you set it to 0, which we will do, it's just white noise. There is no dependence, but the algorithm has to learn that by itself. So here we have, I think, 7 data points, and this is the truth. And then we have 7 data points. It's a 200-dimensional problem. And we are comparing with the ensemble Kalman filter with localization, and ensemble information filter. And visually, you cannot see enormous differences here, except for that the localization has a wrong radius of influence, or not wrong, but it's bad. So it doesn't update as much as the 2 other algorithms. Of course, for this problem, we also know what the ground truth, what an optimal update is, so we can measure how close we are to the optimal update. And those numbers are down here. And what I can tell you is that for all values, our algorithm is the closest one to the update. And similar story, turn down the dependence in the data, adjusting the phi. Again, our information filter is the closest one to the optimal update. Now, because there is less dependence between the data, the radius of convergence of the localization, which is the same for all values, starts working. Now it's kind of accurate. That's good. The most interesting one, I think, is when you actually have no dependence. What you can see then is that the ensemble Kalman filter on the left. So when you have no dependence and you have a sensory point, the information from that sensory point should only update that exact point, right? The information should not propagate throughout the system. What you can see in the ensemble Kalman filter is that it's becoming more and more noisy because of spurious correlations. The information is just randomly propagating throughout the system, so it's becoming worse and worse. Localization and the ensemble information filter does quite well still. And again, ensemble information filter is the closest one to the optimal. So we do the same thing with the heat equation. And the story here that is that visually you cannot distinguish the localization and the ensemble information filter. But for localization, you have to tune things and you have to do arbitrary things and so on. For the joint parameter and state estimation problem, so let's say that we are going to estimate alpha and sigma in this SPD. At the time of writing this presentation, we had not yet started working properly on this, but we knew that at least we can do the same thing as the ensemble Kalman filter, so it should at least be equally good. But we were thinking about something like maybe we can do like a 2-step algorithm or something, because that's what you do, at least from maximum likelihood, like frequentist estimates. If you have a state variable, you will typically estimate that first, especially if it's latent. Laplace approximation on that, and then do some gradient iterations on the parameters, and then iterate through. So maybe we can do something else. We will see. Full recap of this. Filtering algorithms, if the problem is local, it would be really nice to inform the algorithms about this locality so that we avoid noisy updates. And natural assumption is that Markov properties. And amazingly, for Markov properties, for the Gaussian, we are able to build it into our parameterization, which is really, really nice for everything. Yeah, but it turned out it's quite hard to extend this to the ensemble variant, but that's why we built our package, GraphSPME, and this unlocks then the extension to the ensemble variant. And the filtering update seems to be quite smooth and nice and so on. And remember, it's fully automatic. We are not tuning anything. We are just saying which points are neighbors. So it's quite nice. And we have seen examples that it's able to learn, like when you have strong dependence in the system and when you have no dependence, weak dependence and no dependence. And it's able to figure it out. This is Arya. I'm a very proud papa. Do you have a question? It's not an Akita. Okay. Yes. Do you have questions?
There's more clarification. So the slide where you showed the 10,000 iterations and the distributions for the sample conflict, the regular information. If you can show the figure, okay. Once you finish doing
I didn't want to go away from Arya. Like where
you had the 10,000 iterations.
I don't have 10,000 iterations.
Or like when you chose the number, or how when you increase the number of ensemble.
Ah, right. Yes.
Yeah, right.
Right. I did have 10,000 and some.
Yeah, this is just because you said during the presentation, if I understood correctly, that there was still, even with this number of ensemble members, there was a large number of noisy covariant. Like
At least in this problem there are, yes.
Yeah, but because compared to the previous slides, it's still quite like compared to the previous, the other smaller ensemble members, the covariances here are well, with the regular ensemble members are quite they're a lot smaller. So I rather like at one level, to your estimate, your thought, at what height do those various error variances start impacting negatively? At what point do they matter? At what point do they not matter?
So this really depends on the data generating process and the system. And the answer is that I don't want to think about it, which is why we created the
No. Thank you. So I think it's very courageous of you to come as a statistician in a room full of major people. I think we should meet somewhere in the middle.
well, yeah, but the ensemble column filter is kind of in the middle, is a Bayesian thing, but then actually the covariance estimate and the mean estimates are frequentist estimates, right? So it's kind of already.
You seem to start from a priori that the covariance is only containing junk. It's not any information in there that is already used. The examples are like this.
Yeah.
So
in
the cases that say post prediction has come here, there is a numerical model that provides the valuable part of the covariance.
Okay.
That's because you don't know a priori what the covariance is, but the model does the job for you. It will tell you, okay, there's some physics have any kind of complexity. That will show you, okay, these 2 points are correlated. And it cannot tell you the graph, but it can tell you the correlation. And then the job of the matrix inversion is to decluster the observations, because observations can also say in uncontrolled ways.
Yeah. They
are not. Many of them are autonomous.
Yeah.
So then, what's the perspective? I appreciate they could. I see an implication of that in the cases of rivers, where you can simply follow the graph along the rivers.
Yeah.
And the problem is following in their features. So where, say, if you want to use really an informative ensemble from a numerical model, how would you put the information filter in combination with that?
So
assume that you want, someone tells you as part of the contract, there is a numerical model, you have an ensemble, you have to make use of it.
yes. So of course the numerical model in this case is the G, right?
Yes.
So, but I think I don't fully understand how, like when you sample from the prior, the t-1, and then you use the numerical model to go to time t, how can you get the I guess the correlation structure and so on.
Yeah,
From
the
the-
empirical covariance.
Empirical, but yes, but that's you have to estimate it purely, right? Or do you use information?
You only use the empirical information from the G, from the ensemble G.
Right? So, but that will still lead you to spurious correlations, I think.
Yeah, we should touch this one offline. I just make a comment. I actually thought this was really interesting. Just simply because I think, we really need not go too long. But he had described to me a little bit of the use of the sparse precision matrix, and I couldn't figure out exactly how it used and all these things about sampling and things. And actually, I mean, there's something very interesting. But I think it's also the kind of thing that I need to sit down. But anyway, some of those questions that are coming up, I think everyone's going to have to sit down maybe and think a little bit more about them.
Can I have a quick comment?
Of course, you can't hide it.
We have some students, if not, I'm going to talk to you offline.
Okay, yeah, let's you know what, let's take a couple of quick comments because we started a few minutes late. But they can't be too long.
No, it's not long.
Not too hard, which means not too hard.
First comment, I'm not sure, is that a dog or a bear?
Yes.
Okay, so the second comment is that, you know, I did a lot with Gaussian measure using my term type of covariance. And if you look at the term or the TD point of view, the precision matrix is typically a TD operator. It's always sparse, so it's not surprising for me from that point, right? So maybe that has a connection with your if you want to take a look at. The second comment is that if you look at graph, well, when you look at the graph Laplacian, if you make connection between TDEs, right, which is a precision matrix, and the graph Laplacian is a TDE type, right? So it's very sparse. Do you actually can you think about using it directly instead of constructing like for your case?
So I thought about them. So just to the first comment, I thought about the return. I think but that will give you parameterized precision and covariance, right? So I wanted it to be a non-parametric and to get purely estimation, just to make it most similar to the spirit of the ensemble comma picture, because there also you don't have a can have it. To the second comment, I think we have to take it offline because I fully understand it. So we have to do it. But that's actually sounds super interesting. That we really have to talk about.
You were asking a long time ago. You were one for
a comment about when saying no parametric. First of all, sorry, great presentation.
Thank you.
After great presentation, say no parametric, and I understand why you say it. I have the impression that you are moving to a part. I would have liked to see the presentation and see the how you build the connectivity of the graph line. Because that's where the parameters most for me.
So,
I decide to build your graph.
so this is also the question that we are asking in, or people are asking in Equinor internally, like how would you build it? But I guess you have to be like if you're a reservoir engineer, or like if you know the problem, and if you have a field, you almost always use some kind of discretization already of the field. And then you could use this discretization directly, I think, and just define who are neighbors and not. And then if you can define who are neighbors, but that's actually, I didn't mention it, but if you can define who are first order neighbors in a geographical sense or like in a field or something, then we actually, in Graph SPME, we created an algorithm that uses information criterions to then estimate the Markov property of the field. So you have first order connections, but the Markov property might be higher order. So an ARP model, for example, and the algorithm will be able to learn that. So then you only need to say who are neighbors, but the graph that will be supplied to the algorithm will be about who are like conditionally independent, which is combining the Markov order with the neighborhood structure. So, but it's that's the thing that you have to provide, right? So nothing is free, and what you have to provide here is the graph. So that is the thing, right?
And the order of your Markov.
That you can learn from data.
Now we need to stop. Thank you. This is a failure of the session chair, the first time we've ever gone 5 minutes over. But anyway, let's thank our speakers.
I will stop for you because the lag.
Sorry.
Yeah. I'm waiting for. Eduardo, are you ready?
Hello?
Yes, yes. Can
Yes,
you start sharing your presentation?
Yeah, I seem to have lost the stream of the room. I don't know if it's on my side or if
No,
I've
we
ever.
can, because I actually disconnected the USB
Okay.
camera. Yeah, but you can just go ahead. I will.
Okay, let me share the screen. So can you tell me which screen are you seeing? Is it the presentation view or the?
Yeah, it's another presentation. You need to change the display setting. Yeah, to duplicate.
Like,
yeah,
like
I
so?
think now it's, yeah, I think now it's okay.
It's okay?
It's okay.
Okay, so let me just put my laser pointer. Okay, so good morning, everyone. First of all, I'd like to thank Norse and the organizers for allowing me to present my work today. So my name is Eduardo Barrela. I'm a PhD student from the University of Toulouse, currently located at full-time at the R&D department for the field reservoir team at Total Energies. So today I'm going to present you the application of our proposed method for doing 4D history matching using the ensemble smoother with multiple data simulation and flow-based distance to front measurement using streamlines. So this work is supervised by Philippe Berthet at Total Energies. On the university side, Dr. Olivier Toual from University of Toulouse and Surfax. And the work is also co-authored by Corentin Lapère from Surfax and Mario Trani from Total Energies. So the outline of my presentation is as follows. I'm going to start with a brief introduction and motivation for the problem, the proposed workflow, the methodology of the distance to front using streamlines. The case description is a semi-synthetic case application, description of the case, the perturbed parameters that we are going to be using for our runs, or run in this case, and finally the results with the parameter convergence, well production matches, and also the most importantly the matching of the seismic data, so the waterfront matches. And I'll end my presentation with some conclusions and also the future work. Okay, first of all, for the people that are not familiar with the terminology history matching, in oil and gas, is what we call the calibration of reservoir uncertainties driven by reservoir fluid flow production. I'm sure most of you know this, but for the people not familiar with the concept. And so in Total, the areas of interest are twofold. So in one side, we want to have models that are geologically consistent. And on the other side, because we're doing history matching and we're dealing with flow, we want some physical realism to the process of history matching. We want to add also a sense of consistency in the flow domain as well to everything we do. And so The type of workflow that we use currently to do history matching can be, this is an example, it's a standard pixel-based modeling history matching approach that uses truncated Gaussian simulation coupled with ensemble smoother with multiple data simulation. So this could be considered the basis for this work that I'm about to present. And to describe more or less the process in a general way, we start by having some input data with well logs, some variograms describing the spatial continuity of our properties. And for the particular case of TGS, we're interested in modeling facies or rock types. So we have the proportions coming from the seismic of our different rock types. And with this information, we can go into TGS and generate a set of or an ensemble of models to then submit to flow simulation. But we're interested in perturbing this intermediate step of the TGS simulation as the ability to give us a set of or an ensemble of Gaussian random fields that we can use to perturb the realizations from iteration to iteration. And so by taking this together with some engineering parameters, we can obtain a set of ensemble models complete and ready for simulation. We can do the response evaluation of our ensemble. We can calculate the deviation between the production data that we observe in the field and the one that we get in our computer by running the models. And so this is the standard approach, but with 4D, we add another element, which is we are trying to match also the seismic data. So in this case, the waterfront locations for our seismic data. And we want to match these two at the same time. So after having this response, we, in the ESMDA update scheme, we go and regenerate or update the prior ensemble, generate a new set of ensemble members, and we do this iteratively until the last iteration that we choose to run. So this is the basic of the workflow. So as I mentioned, we're using ESMDA, so this is just the standard, the equation for ESMDA is the updating of the prior model parameters with some gain and multiplied by the deviation of our measurement data against the predictions. And so the difference between the ESMDA and the standard ensemble smoother method is just the addition of this inflation parameter that's giving you the strength of the update from iteration to iteration. Yeah, so this is the method that we're going to use on this case. And so the work is focused on 4D history matching, as you know. So it starts from a previous work that was developed at Total by Anaït Abadpour in 2013, where they were using 4D seismic history matching approach that measured the distance between observed waterfronts and predicted waterfronts using the Hausdorff distance. And the Hausdorff distance, the way it works is just calculating the distance between drained regions of the model against the undrained, the closest undrained regions of the model and vice versa. And so they want to match the image on top, the observed waterfront. They get the result in the simulator that looks like this, and they want to calculate basically the distance between these two images. And so they calculate the Hausdorff distance on the observed front, the predicted front. Then by subtracting one to the other, they get a final misfit, let's say for the entire image that they can use for the update procedure. But the problem with this method is twofold. So basically, the first one is that it's kind of a geometrical / mathematical way of assessing the distance between two images that are coming from a flow response. So it might become it's not really fit for the purpose, we think. And also the second one is that the vector of the measurements becomes too large. So it's going to be a vector basically the same size of the model, which in turn will make the measurement the measurement error covariance matrix too big, which to invert is going to be computationally intractable, so unfeasible. And to address this, or to propose something that could address this, this is our approach. So we start by the same assumption. We have a true swept region that we can obtain from the seismic. We have a simulated response here on the bottom, and we want to calculate basically the difference between these two images. So on the true front, we can interpret, sorry, on the true image, we can interpret a front for to attribute to this swept region. We can draw here in blue a front on the limiting the sweepage towards the well. So the water is being pushing the oil towards the producing wells, and it's leaving this swept region. We can highlight the front. And then as we simulate in our reservoir simulator, as we simulate the model, we can obtain streamlines over all of the time steps of the simulation, and namely at the time step of the monitor date for the seismic. And we can extract the distances between both regions, or between the true front and the swept region that we obtain in the simulation, by tracking the streamlines along our model, basically. So we can represent in the true front location at each cell a distance to the simulated front, and that way we have a vector of distances that we can use to calculate. So basically the cost function is going to include this vector of distances that we measure along the true front location. So in terms of under the context of real data, let's say I have to the left, I have an example. It's a CO2 time-lapse data acquisition from SLEP. I'm sure some of you know already these images, but you can imagine it's the same thing for water. So we start by an initial seismic acquisition, and then at the second monitor, we see the difference between the second and the first. So there's already, we can highlight here a swept region here on the model, and we do this over time. So this is the 4D data that we have for our seismic. And if, let's say, we select two monitors of interest here, we want to select this one, call it monitor 1, and this one monitor 2, we can interpret the front here on this seismic data. We can interpret our front and locate it in the grid, basically in the grid of our reservoir model. Let's say monitor 1 is located here at this region, monitor 2 is located here at this region. So now we can do a simulation. We start from the initial saturation and we go progress time step by time step until we reach the first monitor date that we located on the previous slide. And here, as we simulate, we can obtain the streamlines as mentioned before. And also you see here the difference between the saturations that we simulate, so the ones that we are getting from the simulation, and the true front location. We see already some differences. So, but we progress with our simulation until the second monitor date. Same thing, we see the differences here from the simulated against what the true front location should be. But we also have the streamlines here on the right. And so what we do with so we continue the simulation, right, until the end of the simulation. And what we do with this information, with the saturation and with the streamlines, is that we can binarize the saturations. So the difference in saturation from the initial to the time step that we of interest, basically from the two monitor dates. We can binarize this image, discretize from swept regions, unswept regions. And together with the streamlines, we can track the distance between the both regions of interest, which is the true front and simulated front. As you see here, so the true front in black, the simulated front in red, for both monitor dates, and we can obtain the distance between these two elements using streamlines. So ideally for the true front location, if we are comparing it to a simulated response, we'd want to have a distance of 0 measured along all of the cells of the true front. Okay, so we have a 0 over all of the cells measured on the true front, but we need to add some uncertainty as well. And so the uncertainty is added to all of these elements of the measurement data. So we have uncertainty, okay. And with all of this information, we're ready to do an ESMDA run. So we tested this on a semi-synthetic case. It's a turbiditic depositional environment. We have 12 years of production for oil, water, and bottom hole pressure. We have 2 seismic monitor dates for 6.2 and 9.7 years, and the model size of 194 times 23 times 48. So it's a 3D model. Here to the right, you see a top view of all of the different flow units with all of the well locations here highlighted in black. And in the bottom, a 3D view also to look at the complexity, the size of the data that we have in our problem, and also the spatial continuity of the different flow units along that. And so, okay, so for the perturb parameters that we are using in our runs, we are using two types, so dynamic or engineering parameters, and also static or geological parameters. On the engineering parameter side, we're using some fault transmissibility multipliers. So it's basically saying how much a given fault in the model is blocking or allowing flow. Some non-neighbor connections related to sedimentological connections and aquifer connections. Some pore volume multipliers, region transmissibility multipliers, some PI indexes for well productivity. Yeah, here on the bottom, you see a table with the sum up of all of the different types of parameters that we use, together with the number of parameters for each type, the minimum and maximum bounds. And on the right, you see the Gaussian random field that I was talking about that we're going to perturb for each iteration, at each iteration. So, but to go in a little bit more detail how the TGS is working. So, as I mentioned before, but maybe I'll mention here more in detail, we start by having a proportion for each of the rock types in our model. And by running TGS, we obtain a set of Gaussian random values. Here, I'm just showing the first ensemble member. And the TGS, as the name says, truncated, is going to truncate this field given the proportions that we have on our data. It's going to truncate the Gaussian random values to have our respective rock types. In this case, it's just 3 because one of them is attributed to the inactive cells. So we have our facies model here, or rock type model. And with this, we can then populate each individual region with our petrophysical properties. So in this case, porosity, permeability on the 3 directions, and also the net to gross. And by having a set of engineering parameters and also the geological parameters, we can compose an ensemble of models that we are able to be simulated and where we can obtain the response from the production. And so we use this to do a standard ESMDA run with an ensemble size of 100 with 5 iterations and an update of 1/5 alpha. We didn't use localization in this run. But so these are the results for the parameter convergence. So here you see on these plots are for the convergence over the engineering parameters that were used. Some examples, not all of the parameters that were used. Here you see the true value for the synthetic case that was chosen in white with the red boundary. And you see from blue to orange the convergence over the different iterations. You see that we converge towards the optimum value, so the value that we want to match precisely on each individual engineering parameter. So for the NMCs, you see the convergence also on the pore volume multipliers and the fault transmissibilities. So there was quite a nice match to the region of the value of interest. On the static parameter side, we see here the same type of convergence. Here we have all the true model, the rock type for the true model looks like this. Individually, for each individual rock type, the true model is looking like this, the spatial distribution. So for the initial ensemble, we start by having a quite spread initial ensemble in terms of uncertainty of the location of the different rock types. It's more or less smooth all over the model, except for the right regions, which are the well locations in each individual rock type. And we go from this initial ensemble to this final ensemble, which is matching quite nicely the true case in terms of spatial location, also on the types of the proportion. So it's matching quite nicely. This is just showing one layer of the model. Okay. So then onto the well production match. Here are some plots of the production for all for a water cut for all producing wells. You see the same idea going from the initial ensemble in blue, dark blue, to orange. We're trying to match the observed data here in black with the admissible error associated to each time step. And you also see the monitor dates here plotted in red, dashed red, monitor 1 and monitor 2, the specific date of acquisition. And so we obtain a quite nice match on the water cut as well on all of the models. And same thing for the pressure for all of the wells. It's quite nicely matched at the end. But finally, okay, so the results for the waterfront match for the seismic, it's what's the most interesting in this work, I would say. I will start with a mismatch example. So in the left, we have the true case that we want to match. And we have some wells here associated to this saturation at this specific time step of the monitor acquisition, to injectors, to producers. There's one producer here close to the interpreted front that we interpret basically here on the saturation of the true case. This well is associated to it. And on the right, you see, by selecting a run from the initial ensemble, we go over with the saturation, it goes over the interpreted front. And therefore, this well that is associated to it will start producing water much sooner than what it should be producing. And so therefore, what we want to do is to reduce this water and make it move a little bit back to match our true front location. So I'm skipping now to the best match, the final best match result. Here, same thing, you see in the left the true case for this layer, for this monitor date. We want to match this front location, and on the right, you see that we are matching quite nicely on this producer associated to the true front location. You see that the result for the water cut match is quite good, and we're not producing water before the time that we should be producing. So here you see this, this is just the spread of the initial ensemble in terms of the distances being measured on the initial ensemble. So average of the distances and the standard deviation. And you see here the minimization that occurred on the final ensemble. We reduce the distances over the true front. And here on the bottom, you see the same for each individual cell in this front location here. Each individual cell, the distance measured, is minimized on the final iteration here in red, as you can see. So this is just another layer for the same monitor. It's another example for another layer of the model. But it's the same idea. Basically, we're matching the saturations much better. And there's a little detail here. I didn't interpret this part of the front here. I didn't choose to interpret this part. And you see that the mismatch is more predominant here on the non-interpreted part of the front. It's basically where the water escaped. But it's a nice detail to show. And the same idea here as shown before, the spread from the initial ensemble to the final ensemble, the minimization that occurred for monitor 1 on layer 14. So for the second monitor, we have a new well that is associated to this front that I want to highlight. You can see that the matching of the seismic of the saturations comparing to the truth it's quite good as well. The minimization has also occurred quite nicely. We start from a wide spread to a very almost matched spread all over the entirety of the front location. And you see here on the second layer for monitor 2, you see that the result is almost accurate, the match. It's a really nice match. So the well is located to the west of the front location, and you see you see that it was already producing before the seismic acquisition, but not that much because the water is here, and so it's captured quite nicely this behavior here together with matching the well production data. Yeah, and finally, it's just the same illustration of the initial against the final ensemble in terms of the distance being measured. It's the minimization that occurred, which was provided us a nice match at this well. So I wanted to end. This is all I had to show to you here today. I went to end with some conclusions. So we showed this 4D seismic flow-based method of measuring waterfront location using streamlines and applied it to a large-scale 3D model. There are some advantages to this method, namely that this method is quite straightforward to be used, and the streamlines can be obtained directly as a post-processing from flow simulators, so it's easy to use. It was successfully applied by using it in conjunction with an ESMDA history matching workflow. It has some pluses. We are able to assess the flow path and direction in direct contrast with other geometrical or grid style approaches, as the one showed before for the house of distance method. And it also has the advantage of greatly reducing the amount of data for mismatch calculation. So we go from the number of cells in the model in terms of the measurement against the observed. We go from the number of cells in the model to the number of cells in the interpreted front. So it's quite a substantial reduction. So for future work, we're planning on applying the method to a real case scenario. We are also looking at some other geomodeling approaches that could add some geological consistency to the models that we have. And we're also going to investigate on localization when when we will apply to the real case scenario. Yeah, and so that's all I had to show. Thank you very much for the opportunity to present, and thank you, Norse, and the organizers for the very nice event. Thank you.
We are a little past, but not because it's not his fault. So if there's time for a few questions. One comment I might make is this talk really showed a bit more like reality. This wasn't a real case, but it shows a bit more what kind of data assimilation goes on, as opposed to when we show those little problems where we're estimating permeability or something. This is a bit more like what might really happen in data assimilation.
Yeah. Maybe I can ask a quick question. So I just wonder what kind of challenges you might expect when you do localization. Because I saw that you didn't do localization at the moment, but you have such a plan. Do you have any idea?
Sorry, could you repeat?
Yeah, I mean, I think you have a plan in doing localization, but do you see any particular challenges?
I can foresee some challenges. Quite honestly, I don't really have a plan at the moment. I haven't started looking at it, but I'm predicting that maybe it's going to be necessary. But to be honest, I still I have no idea yet what I will try to implement. But for sure, this talk was a great opportunity to already know a lot about the state of the art in that front, basically, on the localization methods that are available and being currently investigated. So at the moment, I don't really have anything to tell you. I'm sorry.
Fair enough.
Well, thank you very much. That was. Let's thank our speaker one more time.
Thank you.
I need to find your presentation.
So the next speaker is Mohammed Nezadali. It's going to be about multi-level data assimilation.
I think I need to talk. Can you stop sharing your presentation? I'm not doing it right now. I'm going to share it.
Please, we can try the mic now. So.
It's good that you put on the mic. This is your presentation. And yes, here you go.
So does this
thing
work?
Yeah, try that. And while it's presenting, we need to check out before 12 o'clock. So if you guys didn't do that yet, then you can use the break to do that. Yes.
Okay. So yeah, this is Mohammed Nejadali. I am a PhD student at Norwegian Research Center and at the University of Bergen. And I've been working on multi-level data assimilation together with my supervisors, Tuhin Bakhta, Christian Fossum, and Trond Manset. And I'm gonna give you a brief description of what we've been doing during my PhD project at Norse in the past 2.5 years or so, let's say. So yeah. And by the way, Tony, you've been a very good inspiration for me, source of inspiration. So I will keep my talk with the minimum level of equations, as opposed to many of the people who are presented here, even though we are doing method development. So the outline of my talk is, as you see here. I will start with a problem statement, then I will give some motivation on what we are doing and why we're doing it, and which is multi-level data assimilation. And then I will explain what do we mean by multi-level models and multi-level data, which will be followed by a brief explanation of some algorithms that we have developed. And then I will show you some numerical experiments, and I will also explain the current state of our work and what do we plan for from this point on. I hope it works from now on. Yeah. Okay. Oh no. Which way is it? Okay. So we consider the parameter estimation problem using spatially distributed data. The Bayesian framework of ensemble-based data assimilation is considered as well. And throughout the presentation, the parameter random vector is denoted by Z. The model forecast vector, being a nonlinear function of Z, is denoted by Y, and the noisy data are denoted by D. Yeah, these are all we need, I guess. And as for the motivation, I can say that large amounts of simultaneous data, like with the 4D seismic data, which is people who are working in petroleum domain are pretty acquainted, but all you need to know is that it's plenty of data, and even it's inverted seismic data in our case, which is large amounts of grid data, spatially distributed data. This kind of data enhance the negative effects of Monte Carlo errors in data assimilation, and one of the common results is underestimation of uncertainties. So the conventional treatment is distance-based localization, and which regularizes the problem, but by assuming that the correlation between a parameter and a datum decreases by increasing the distance and vanishes when a critical distance is reached. So this, assumption may not generally hold, and this is not, this does not have a very firm statistical, let's say, ground, let's say. But one thing that we could do instead of localization is increasing the ensemble size. But since we have a limited amount of computational resources, we should, if we want to increase, we should just use, let's say, less complex models. So lower fidelity models, let's say, will reduce the computational cost and therefore allow for a larger ensemble size. But they will also increase the numerical errors. So what we are trying to do in multi-level data assimilation is to obtain a better balance between these Monte Carlo errors, mentioned, and also the numerical errors by combining models with different levels of complexity. That's it. Okay. And okay, in our project, we consider a spatial coarsening of the numerical grid as the way of making, models less complex. And the reason we are doing it is because it's a very efficient way of reducing the computational cost. And okay, these figures that you see here are some representation of different, let's say, levels of coarseness. Schematic of that. And because we are going to assimilate. Somebody asked me something. Okay. Okay. Yeah, sure. Yeah. Okay. So obviously, the most accurate model is the costliest, and we cannot afford many simulations on that level. And the least accurate model is the least costly. We can afford many simulations. And this is, I mean, this can have many number of levels, so it needs not to be only 3 levels. But yeah, in this case, it's for the sake of just explanation, I use 3 levels. And the model forecasts will be, because we are after spatial, I mean, assimilation of spatially distributed data, the model forecast will be also in different, let's say, resolutions if we use this kind of model, as you see here. So, and okay, and the data, we assume that it will be given to us in the finest level of resolution. But since we are going to assimilate it for the models at different levels, so we will have also multi-level data. So we have to also in some form convert or transform the data into different resolutions. And yes, again, these are the notations that we use, and we use also a linear transformation for transforming the data from the finest level to any arbitrary level. Okay. So yeah, as I mean, I will briefly go through what we have done. So as you know, the ensemble, I mean, in ensemble-based data assimilation, the algorithms are, I mean, either assimilating the data simultaneously or sequentially. I mean, examples of simultaneous data assimilation would be obviously ES or ESMDA or iterative ES, I mean, NRML. Or, I mean, and examples of sequential would be EnKF or EnKF-MD or things like that. So regarding we can just expand it through the domain of multi-level data assimilation, and we've done it. So in simultaneous multi-level data assimilation, we consider assimilating all the data, let's say, together using, I mean, all the models, I mean, in the same step. So, okay. In this novel approach to multi-level data assimilation, we developed an algorithm which draws heavily on ES. But I mean, long and short, we, I mean, in the update step, we use this law of total covariance to formulate multi-level covariances. And for different levels, we okay, have different Kalman gains and so on. But I mean, I'm not going to go through the details about this one. But I mean, this is the paper. And yeah, I saw this QR codes, fancy stuff from some of you did it, so I decided to add it as well. I don't know if it works or not with your phones, but and we also developed an iterative version of this algorithm by formulating this I mean, posterior logarithm of likelihood and then Gauss-Newton algorithm. So the first step is similar to the one, the smoother, and then after, I mean, the next step, the algorithm changes. And we also compared, in this paper, we compare them to the conventional methods of history matching, let's say. Okay, we also, because, I mean, we also developed some methods for multi-level modeling error correction schemes, but first I have to explain what do we mean by multi-level modeling error. Because we have, because we use, let's say, coarser models, we also entail, we also include some more modeling error. By more modeling error, I mean, okay, there is some physical reality, let's say, I mean, let's say, R is a spatially varying property, and there is a difference between this, special varying property with the mathematical model. So this is some error that some modeling error at the first place, and then there is also some modeling error between the mathematical model and the continuous form and the discrete form of the mathematical model. But all of this up to this point can be pertaining to the all the ensemble-based data assimilation methods in general. That's not what we are after in correction. What we are trying to correct is the additional error that we add by using coarser models. So we define this multi-level modeling error by the difference between the upscaled fine simulations, and the coarse simulations. So this is defined by multi-level modeling error, and we try to come up with some correction schemes. The idea was to simulate some of the ensemble members in using several of these models, let's say, and by the insight that we get by using all of these, by computing the actual multi-level modeling error for these sub-ensemble, let's say, formulating, and setting a set of assumptions, we came up with 4 different correction schemes, let's say, and we just published it here in case you're interested. So yes, and in the last part that we are almost done with it is developing this sequential multi-level data assimilation algorithm, and in doing so, we firstly use the models with the coarsest level of, we use the coarsest models, and then assimilate the corresponding coarsest level of data, and then we use the less coarse model, finer models, and finally we after several steps we use the finest models and the finest level of data, let's say. And there is a specific motivation to this, to the idea of using the coarsest model first, and that is okay. If we have a less short range fluctuation in the parameter field, some papers show that the problem becomes less nonlinear, let's say, and by using the coarse models first, we just get a, let's say, rough solution to the inverse problem. We get to the vicinity of the problem, the solution of the inverse problem, and by using the finer models afterwards, we just zoom in on the solution. After some steps, let's say. And there are some similarities between this sequential multi-level data assimilation algorithm that I explained and ESMDA. And Sungil just explained ESMDA, so I'm not going to explain it in very much details. Okay, the idea is that you sample from the prior. Okay. Then so use these fine simulations and fine data to, and of course you inflate the data error covariance matrix, and then use the ES update once, and then you come up with the posterior of the first step, and then the posterior will be the prior for the next step. You use again the same models, the same data up to a certain number of times, and then you will come up with your posterior updates at the end. And the algorithm that I explained was pretty similar to this. But in the first step, we use the coarsest model and the corresponding data. And these boxes that you see here are somehow, let's say, representative of the size of that sample. So because we can afford a large number of, a large ensemble in the first step, we okay, we have a large box over there, and then we update in a pretty much similar fashion, but using let's say M1 and D1, and then come up with the posterior. We sample from the posterior, use M2 and D2, and so on and so forth. And at the end, we come up with this, posterior estimates of the parameter field. Okay, so I briefly explained this sequential multi-level data assimilation, and I'm going to present some experiments which are not published yet from that for this algorithm. And so in that, in order to do that, it's going to be 2 experiments pertaining to subsurface flow. And the unknown parameter field is flow conductivity. In petroleum terminology, it's permeability. Observation data is grid data at 3 different times, and it's inverted seismic data, bulk impedance. Each experiment has 4 algorithm runs. It's SMLES, the algorithm that I explained. IES with localization, so it's NRML with localization, and ESMDA with localization. And there is also this ESMDA ref, and this is the gold standard that we're going to compare all of these algorithms with. And this gold standard will be vanilla ESMDA with an exceedingly large ensemble size, 10,000 ensemble members. And this is run to obtain the best data assimilation result that can be obtained by ESMDA, and because of the similarity that it has to our algorithm. And this ESMD, I forgot what I wanted to say at this point, but it was a good comment. Yeah, anyway. Okay, so I'm going to go through the do we have time? Or?
Well, I was just going to point out to you, there's about 7 minutes left till the end of your,
Okay.
That should include some discussion.
Yes, but I was not, I started not at the time, but okay, anyway. But that's fine. I will just skip one of these. Okay, I will skip case 1. And I will just include, this is more interesting a bit. So this is a 2D reservoir, let's say, with 2, let's say, we call it permeability zones. And so this is based on 2 variograms, and there's a smooth transition between the 2 fields. Okay, the results that we obtain using ESMDA ref, as you see, is arguably similar to the algorithm that we have developed. And ESMDA with localization and IES with localization are not that successful, let's say. And this is even more clear in the variance. This was the mean field, and this is the variance field of the parameters, of the posterior parameters. And it's even more clear here. But there is something that we should notice, that we still underestimate the uncertainty in the parameter field. So the scale is different for SMLES. Yeah, but there is also posterior model forecasts, and in this case, again, the algorithm is performing arguably well, but in the posterior model forecast, even the variance field is very, very similar to ESMDA ref, so it's doing a very good job in this case, and it doesn't underestimate the uncertainty here. So yes, and at this point, we are trying to implement what we have already developed on the realistic cases. So, I mean, and we should customize the MLD algorithms for realistic cases, for example, by, I mean, inversion of large correlated covariance matrices by the help of SPDEs. I mean, yeah, it was, I mean, Natsian SPDEs, covariances was discussed a bit earlier, and hybridizing MLDA with localization. So because multi-level data assimilation, the multi-level phase is mostly focusing on the forecast part, and the data and the localization is on the analysis. So they can simply be hybridized together. And yeah, we are at this point implementing them on realistic cases at this point. I'm trying to let's say just develop some simplistic but robust grid coarsening and upscaling techniques, so that's I mean, so as to be able to investigate the performance of these algorithms on realistic cases. And the case that I'm working on right now is UniSym1, UniCamp, and yeah, that was pretty much it. And yeah, thank you for your attention. Questions?
Hello, thank you. My reservoir engineering is lacking, but
Mine too. But
so first you have a large ensemble, right, and a cheap model.
yes.
Yeah, so you make a lot of prior realizations first, yeah.
Yes.
And you end up with a lot of posterior ones.
Yes.
Then the next iteration you need less.
Yes.
Realizations, basically, right?
Yes, that's true.
How do you kind of go from a lot of posteriors to a few?
I mean, we just randomly sample some of them. I mean, in the ESMDA, you just take all of them into next step, right? So, but
yeah, but they're from a different grid, right?
The first. Oh, okay, that was a very good comment, actually. The grid coarsening, I forgot to talk about that actually. The grid coarsening and upscaling is assumed to be part of the part of the forward model. So the parameters are always kept at the fine model. So yeah, but the forecasts are of course in different resolutions. So thank you.
Thanks for the talk. It's very interesting. I'm wondering if you do data simulation for each level, so you want to optimize the parameters in the filter, for example, localization. And now you have multi-level, then you need to fine-tune more parameters. How do you do that?
I'm not sure if I understood the question.
So when you do the data simulation step for each level, like each resolution,
okay,
do you tune the like these common filter or common smoother parameters, like
okay.
parameters?
Okay, I mean we use okay, for each of the levels we use a different Kalman gain, let's say. So and I mean at each at least at for the algorithm that I explained, you don't need to really worry about that because you actually are all you should assume is that you have that model M at a specific level L and the data which are already transformed to that level. So you simply do something very, very similar to ES update in that specific level. So, I mean, you use the cross covariance between the parameters, which are in the fine level, and the forecasts at any level. And then, I mean, the rest is the data error covariance matrix is, I mean, you multiply it with that transformation term from both sides. So it will be already transformed. And the model forecasts are already in that resolution. So you don't need to really worry about much. Ensemble smoother, I'm sorry, yeah.
Yeah, good talk. More of a technical question. So when you said that your observations are for the densest grid, right?
Yes.
Yeah. So how
the original data is given to us.
So when you transfer that data into the less coarse grid, sorry, how do you transfer the observation errors?
Okay, we consider a linear transformation, and with, I mean, okay, we already have had a data error covariance, I mean, data error uncertainty as well corresponding to that, right? And when it is linear, you can just multiply it from both the data covariance from both sides with the transformation, linear transformation term, and then you have the data covariance for that one.
Nice talk. I don't see you cite many reference on multi-level, multi-color method, but I'm sure you're aware of that, right? And one of the main challenge in multi-level, multi-color method is how many samples on each of the levels, right? And that actually based on the depth. You need to have a reverse error estimation in order to actually do it correctly, right? In order for it to be efficient and to be accurate, then you need to determine that. So I see that you show two charts, one with, I don't remember, the sequential one where you have different size of ensemble, right? And can you tell me how do you determine these ensemble size based on what?
I mean, these, and I mean, the ensemble sizes are determined based on, we consider a certain level of ensemble for, this is just heuristics. This is not very, this does not have a very good statistical ground for this. But we consider a certain number of ensemble size for the finest level, because that's the final sampling is going to be from there, right? So, and then consider increasing it for, again, then that when you just decide about that, then you, based on the rest of your resources, you decide on the next finest level, and then so on and so forth, so that it will not be, so that the uncertainty will not be underestimated. But that was a good question, actually. We, in our case, we do not really measure the data, multi-level modeling error very rigorously, let's say. But we assume that the variance that we compensate for is less than the bias that we add for. So that's the assumption.
I think it's okay. Heuristic, if you don't have anything, then heuristic is okay.
Yeah.
I wasn't trying to.
We have not done any optimization or any rigorous research on that. So.
Yeah, but I think you spend some time talking to some mathematicians. You should be able to come up with some error estimation. You don't actually need to do real rigorous, right? But some estimation going to help you, instead of making an assumption, like you said, estimation will allow you to actually determine more in the principal way to determine how many samples for each level to assume to guarantee some accuracy and the speed.
Yeah, we have tried to address that question by formulating this correction schemes, and but that was a good comment.
I just want to add, this is not exactly like because we have a paper from previous to this work where we did this, we analyzed errors, and so that we cannot do standard level on the complex restaurant because we cannot get the coupling.
Yeah,
so that's what we came up with.
Right.
We need to have a break. We need to, for some reason, your hand never gets spotted.
Let's go for a break. Thank everyone.
They must think Mohammed is and come back at whatever. 11 minutes. I'll use this one.
Do you have any? Yeah.
I think so.
Oh, you sent it. Oh, okay. I didn't notice that. Sorry. I need to confirm how painful is top one. I don't want
I mean, that's the part of the previous part because there is lots of implementation trick that you have to do?
My question, maybe you know, is downscale, upscale, might introduce some sort of error in the calculation. Actually, it's already there. I forgot you
Okay,
that
okay,
yesterday.
okay, yeah. So how do you pull this on?
Yeah, it's like this.
Oh, wait, so it goes on like
Yeah.
this?
Yes.
No, wait, this can't.
It's actually the right.
It is. Oh.
And let me
Okay, it's
open.
like wearing glasses.
Yeah.
That you make like
And a small tick from Ian is that you can do this. If you see this thing popping up, just click this one, hide floating meeting control. Okay, then it's going to disappear. Yeah. Let me find yours.
Who's the session chair? Is it?
It's Rolf.
Yeah, but I know you've been taking care of a lot of the things.
That's okay. So this is your presentation.
So they.
Yeah, and
so
yeah, you can try that.
Yeah.
I'm going to put that in the screen mode.
Okay. So first of all,
I only have this one. Because I don't want.
and I think, and the pointer is just.
The pointer is somewhere.
I'm pointing the wrong direction.
And just in case it does not work, use this up and down. This up and down.
Yeah. Okay. The up and down.
I think everything.
That's good.
And I can mute, or maybe I don't have to mute.
Yeah, I'm already.
It's okay. I mean, I just leave
okay.
everything here. You don't have to do anything else. Okay.
Oh.
That will be fine.
Problem that is Mac itself and it's when it's in one, so I have to really expand it to the whole thing.
If it's a box, it's
Much easier, but I mean, for this, we are, I mean, it's under the.
Yeah. But I think it's possible.
I hope.
I think you will very interesting because you correctly solve the problem of cross correlations.
Yeah.
I think very nice.
Yeah, thank you very much.
I think we will check out. Yes.
Everyone's gonna go check out the long line. I'm checking out. Like you.
For this method, the effect it didn't have that strong problem with the levels. For the method, yes, absolutely. What else they could come there?
Yeah, it was really good.
Strong,
But,
allow you to.
Thank you. You should read this in the mirror.
Well, I think what we need to do, I want to check out.
I asked him.
And go through and compare a little bit.
You're speaking to the.
Realistic ones, still we cannot, and I also explained that maybe in order to keep saying now, we may include localization there as well, not be super important.
Yeah, no, it's of course in the next level, so in the multi-level, it is generated. Multi-level. The idea is that between consecutive levels, we will have strong top. That's allow you to actually put a hard work on the lower level. Right? Then you should do a little bit in the direction of the next level. So I don't like it. I don't think that's how to start. You have to do a lot of work on the process level. That's work on the next level, and yet you still can get the same accuracy or efficiency. And that was one of the key that allowed me to have that. I don't know how. What does it actually for your you can do whatever you want, but though it actually do anything, that's this would be okay. That's why I think you're comfortable. Absolutely. Yeah, I appreciate it. Okay, that's good work.
All the different levels after the first from the second distribution. Right?
I mean,
Yeah, but there's also a question of if we actually start, you don't, but we actually start with comparing. We sample from that. No, thinking that before, since what Mary messes bring up the word. No. We don't form that covariance matrix. We have covariance matrix, and then from that, we get for the error of second model, for different parameters values.
So just that
For the observation of the simulated model at a different accuracy. Another different things.
Some that we don't really like to talk. So very refreshing.
Yeah, or estimating because maybe it's cheap to estimate, then you could like just refine in a part of the parametric domain or parametric distributions. Okay, they're really more fine solutions, while another part of the domain.
Yeah, couldn't see the difference.
That's Yeah, and that's for the grid space, but I mean also for the particle space. Because the error impacts also on the some parameters, also a course grid can have relatively better results. So when you scale up with the
e-commerce
but you might need that many solutions. For certain parameters.
Or maybe like I do, more with figure like and then as you start speaking, you pretty much be sure Chardon be running over with my first fingers, and by the time he gets to me, question's finished.
I think it's the question of running check out. Also that no, I don't want to wait. They're checking out. They lose out.
They lose out that we have
I can see if the queue is still long.
He's got two talks about the flood.
No, I know, I agree. I'll start talking on that.
I think so. No, he's watching for question in the audience. Or in the online. Not so big. I don't do.
No, I don't. I never.
Yeah, it's too much, and we cannot go over there because I that's
I mean, I have my laptop. I could actually watch the question.
Yeah. No.
Checking out the foundation or looking around, there's nobody at the counter.
Oh, okay. Stop.
Okay, I think that I'll call it.
What time is that?
Mine was just a minute.
Okay.
I don't know. When you lead it, correct? And you lead it, Mark. Yes. Nice. That's the beauty of the.
I love these green lasers.
They were quite visible.
Oh, they're really good. Yeah. I mean, I would spot just for. Yeah. It's like having a whole layer. I'm going I'm not going to find it a lot.
this triangle measurement, this workshop is about generating health.
Yeah, I think we are about to start to find the seats. So the next speaker is Dean Oliver from Norse. So with that, I think I'll just give the word to you.
Thank you. So this talk actually covers topics that, by the end of the conference or workshop, we've seen things like this previously. I just want to say I put the word hybrid in front of this, and I want you to know it's not a hybrid particle ensemble filter, or it's a hybrid in the sense that the same that Hung talked about, where he talked about estimating a gradient that was partially from a neural network and partially from the adjoint, and you almost could call that a hybrid. But mine is going to be, in a way, partially from the ensemble and partially from an analytical derivative. So that's the hybrid aspect. And the hierarchical has to do with uncertainty and covariance. So it's something we don't normally do. And can't get that to work either. There. So this, in contrast to a lot of the people who estimate states, this is a parameter estimation problem, and parameter estimation problems have some, some aspects of them are quite different than if you're estimating states, including how you do localization and what you might want to estimate. In our parameter estimation problems, we still are interested in the states. This is actually a partial differential equation where we're actually solving for example, saturations and pressures in a porous medium and measuring saturations. So those are what you're measuring, but you're updating the parameters. And once you've updated the parameters, then you can solve for the states. Okay, so it's a partial differential equation, it's these coefficients. And some typical examples, the one I'm going to show is its injection of water into an oil reservoir. So you're displacing oil with water. And you're making measurements at a few individual wells. So what you make measurements is of the state at a well, for example. But other applications would be injection of CO2 to sequester it if you removed it from the atmosphere, or you could be looking at transport of pollutants in groundwater. So these are all porous media. And the thing that makes them sort of a little bit difficult is these parameters you're estimated are spatially distributed. So you have lots of them if you've discretized your model. Okay. So in this type of inverse problem, if you're doing Bayesian, you have to specify a prior. We specify a prior for our model parameters. So this is saying if permeability is uncertain, I have to say, is it spatially correlated? How is it spatially correlated? What's its variability? Things like that. So that's what I have to specify. And I would say often use Gaussian. You could see that real example, or not real example, but the example from Total wasn't using just Gaussians, but Gaussians were in there. Okay. And so if we use a Gaussian and we fix the covariance, we fix the, so we fix the covariance type, we fix the range, we fix the anisotropy, and we do it wrong. And I say wrong, if we do it in a way that's inappropriate for the data, then we're going to have a very hard time matching the data. So that's the situation we're in. So this shows, I'm going to show all my examples on this particular application. So it's a 2D porous media. You're looking down from the top. So here, these are producing wells. This is producer 0, producer 1, 2, 3. So there's 6 producers. Those are going to be where you make observations. So you're going to measure when water arrives and also how the water evolves with time. And the water is coming from these 2 injectors. And then the color scheme here is showing permeability. So permeability is a property of a rock that tells you how hard it is for fluids to flow through them. If it's very permeable, it's really easy to flow through. If it's low permeability, it's hard. And so, for example, this right here is a low permeability. Let's say call it a barrier. And you can kind of imagine if you injected water here and it has to go somewhere, it's going to have a hard time maybe crossing over this barrier. It's going to preferentially go down maybe to this. And so that's the kind of thing that's going to go on. And so this is in a way is our forward map. This is our from our material properties, which are the permeability, to the things we observe. And this is what I'm going to say is this is what a bad prior might look like. Someone might say, I've chosen my covariance poorly. For some reason, I think there's these kind of channels, but I think they're oriented north-south. And so I just sample my initial ensemble from that. Okay, and so just kind of what happens. I know you see so many of these plots, and I know they can kind of be wearing on you, but this is showing after you've done data assimilation. So you've adjusted the permeability field as best you could to observations, and all these little dots here are showing observations of water saturations at particular producers. So you'll notice, for example, it was just oil, no water, no water, no water. And finally, after about 50 days or so, then it starts making water. And this is just because there's a long delay. It has to first displace the rest of the oil before it gets there, which you'll notice some of them break through much faster, some are slower. The thing I wanted to point out is if you use a bad prior, you simply cannot match. You simply cannot match some of your data. Okay. And this is just what happens if you use a better prior. So it's it's a much tighter band. We're looking at, this is 100 ensemble members. They've all had different permeability fields after data assimilation, and they're all matching the data. So it's a very underdetermined problem. Oops. Okay. So I'm going to say how I'm going to add how am I going to characterize the uncertainty in the covariance? And I'm just going to use a very simple model. I'm going to use one called geometric anisotropy. And I'm still going to assume that my covariance is spatially stationary. So in that, what I mean by that is that the covariance of the model parameter, and M, it means model parameter, and this is kind of a geophysical inverse problem notation. So M means this means model parameter at location X. Now X is actually a physical location. Compared to that, the covariance with the model parameter at X prime is only a function of the distance between X and X prime. That's what I mean by stationary. And then, but there's a coordinate transformation that says the distance is different in different directions. And so you can see here, there's a rotation of the coordinate system, and then there's a stretching. So one of the distances gets stretched. So you might say this could be an uncertain parameter, this orientation, that's the orientation of your covariance, and this stretch, how much longer is the range in one direction versus another. And there'll be another, and this is a third parameter. It's this rho, which is my range of my covariance. So you could have very short range covariance or very long range covariance. There's other things that could be considered as uncertain, and I just didn't include them. Okay. So that sort of defines what I'm thinking is uncertain. But if you tried to just say my model parameters, let's say permeability, and my hyperparameters, the parameters of the covariance, if you just said that's what's uncertain, you could actually say, well, this M conditional on these, that's a Gaussian, okay? But these are not jointly Gaussian, okay? It's only conditionally Gaussian. And so if you tried to do what you might think of as, and some people have tried this before, they generate realizations of M, and then they just try to update them as if it was Gaussian, and each one has a different hyperparameter. It's a mess. You're mixing things that shouldn't be mixed. So what I'm actually going to use is a parameterization, and this is the hierarchical parameterization. It's called a non-centered parameterization, and this is historically this is called a centered parameterization. So this non-centered parameterization, we're going to introduce instead this variable z, and z is this standard normal Gaussian, normal and Gaussian seems the same, standard normal IID variables that connect my covariance matrix. So C sub m is my covariance matrix. This is like a Cholesky method of generating realizations. So I'm just, if I've got my model parameters, or if I've got my Z, I can generate model parameters, and all these parameters fall in here. Okay. So that's and by the way, this type of use of this parameterization for inverse problems has certainly been done before. Lassi Roninen in Finland, and some people in Andrew Stewart's group have done this kind of parameterization, including spatial. So this just gives an indication of now we're going to generate prior realizations from our prior, and now they actually have kind of this nice characteristic. They've got a lot of they've got different ranges, different orientations, and so it's no longer now there's no longer such a big danger of doing it wrong, because certainly you would hope, I mean it's not true, but you would hope that somewhere the truth might fall in one of these, or one of these is closer. This just shows. This is my, I have a prior on my orientation and a prior on my correlation length. And then it's a little bit misleading. The actual length scale here is 1 on each side, and I'm showing it in terms of grid, but my the dimension of my model is 1 by 1. So when you see a correlation of 0.8, that means the correlation length is something about 0.8 of the model. And by the way, feel free to stop me if something's not clear. I'm trying to go sort of slowly to make sure, because the notation's different and everything's different than what a lot of people use.
Can I interject?
Yeah.
So you say one reason for bad priors might be that the hyperparameters are bad. Let's say that's one characterization of a bad prior, at least. And then you say that rather than estimating M plus hyperparameters, you want to estimate Z plus hyperparameters.
No, I actually want to estimate M, but what I'm just saying, I can't put it into I can't use it in a standard iterative ensemble smoother by putting M in with the others. I want M. I don't care. I mean, nobody wants Z. Yeah, if I gave Z to a reservoir engineer, I mean, it's independent random variables. It's just it's what I have to do to reparameterize to solve the problem. We could talk later, but it's a bit like if you use truncated Claire Gaussian and you have a latent variable, you don't care about the latent variable, you care about the. Okay. So the posterior, I'm assuming that. Oh, sorry, and I made a small. I neglected to say. Now I've suddenly got X. X is not the spatial coordinate that it was a couple of before. Now X is the collection of Z and those hyperparameters. So it's everything all together. So I've lumped them. So this is now all the Z's, which is maybe 1 per grid block, and those hyperparameters. And so the posterior distribution for those given the data. And now it's you can see I'm assuming that these are all that the prior distribution is Gaussian on all of them. And I do that because I'm going to use an iterative ensemble smoother. But I've actually, to be honest, the variables themselves are not Gaussian. I've done a log transform before I've done some of that. So again, it's a little misleading what I've done there. Here's my likelihood up here. And you can see that I've got a data mismatch. And now my, this G, our lowercase g again, is my mapping from the parameters to my data. Okay. And now it's gotten a little bit more complicated because it used to be in a normal one, it would be G of M. So it would be the flow simulator. If I put in permeability, I would get water saturation, for example. Now it's G is a function of X, but so it's got this additional, there's a composition. Okay. And so the reason I show this is if I wanted to find the MAP, the maximum a posteriori model, I would just take the logarithm of this and minimize that or the negative of it. We're actually going to use an approximate sampling method. So approximate sampling from the posterior is based on minimization of cost function. And that cost function looks a lot like this, except that you'll see I'm taking the difference between by minimizing the difference of the predicted data that have been now perturbed against the actual observations. And instead of trying to stay close to the prior mean, I'm going to try to stay close to the prior observation. And for those of you that aren't familiar with it, it's accurate for, it's correct for linear Gaussian problems. That's why I'm using the Gaussian prior. It's an approximation. One of the nice things about that particular approach is in a multimodal problem, it will actually sample more than one peak. It samples the peaks. It simply doesn't do it all. The weights won't be correct. Okay. Okay. Now for history matching, so if I wanted to actually solve that, to do that minimization, I would probably use a Gauss-Newton type approach. We don't usually have access to those derivatives. So we tend to like to use iterative ensemble smoothers. That actually looked quite natural approach for an iterative ensemble smoother. This notation is just a little bit messy, but yeah, I'm going to cancel. Sorry, who knows what I pressed? And now I can't cancel. Oh, there, sorry. So you can think of this, you can see I'm just making an iterative change. This is a Gauss-Newton it's a Gauss-Newton update step. Here's my data mismatch. This is, I'm saying it's like a Kalman gain matrix, although it's iterative, so it's being updated at each step. And then there's some other terms in here that have to do with staying close to the prior. So there, yeah.
This is just a calculation. So you said that in the original picture, the figures you showed, X was the placement on the grid. Here it isn't. So this is just so. Are you now, when you're fitting this, are you fitting this for the whole? Is this for the whole grid, or is this?
This is for the entire grid. So this X, sorry, X is this is my vector of my at the L+1 iterative step. This is my vector of all of my Z's and rho and phi and alpha. Okay. And it's actually evolving, and then I'll stop. When I stop, I'll have my actual estimate. Okay. So this is a very traditional. The reason I like this is just the way we do updates, and it's a very effective. It works really well for reservoir models. Okay. There's other formulations that work too, but iterative ensemble smoothers work remarkably well in a lot of reservoir problems, and that's why we use them. Okay, so I'm going to show a little bit of a fluid flow example. I'm going back to this one, and just to remind you, we're going to make measurements at these 6 locations. This shows what the time series looks like at those. These are the actual observations. And in an ensemble smoother, unlike an iterative ensemble, unlike a filter, we're actually going to bring in all the data at one time. So we're going to try to match all that data at one time, although iteratively. And you can kind of see this number 5. So this, for example, that one is this one. It breaks through really fast. It's sort of like I said, that there's a sort of a barrier here. The water has to go somewhere, so it's going to race down here to produce a 5. So you can kind of see, and you get some idea in a way of what a linearization would look like. So because you're getting an idea of what would an observation be sensitive to. Okay. But computing adjoints is something you don't like to do all the time. Okay, so I went ahead and did this as an iterative ensemble smoother, and like I say, they work remarkably well. And in this case, it was surprising. It actually didn't. It worked remarkably badly, is what I would say. And so what you're seeing there is this is my prior predictive distribution. So there's my actual data. I run my my models on the prior. And I plot each of them for each of these wells. It's not all the wells. And then after a history matching, I show the posterior distribution of predictions. And it's not a whole lot better. And it's certainly not where you would expect. Now, this is, I'm not showing error bars, but you can kind of guess what the error bars are here, just because these are observation errors and the response is smooth. So you can definitely would know that is not doing well. And it's not doing well just because I stopped after 4 iterations or anything. It's not doing well because it's simply not converging. Okay, so this just shows my a square of the data mismatch for everything, and it just decreases a tiny little bit and then stays about constant. And nobody in an oil company would spend this much time, iterating that many times. Okay. So there's a number of reasons it doesn't work. But I'll say one reason it doesn't work is if we look at sensitivities. And this becomes really a highly nonlinear problem when you do this covariance, when you bring in these hyperparameters. So this, if you can imagine a simpler problem where actually you observe the permeability at that one spot, you can see where this black dot is. And then you say, what's the sensitivity of that measurement of permeability to Z? Okay. So now Z is independent, it's the field of independent Gaussian variables. And it's actually, now by the way, this is for one realization. You can't, okay. So it's only dependent on the Z's along this axis. And the reason is because that's the way the permeability field is oriented. And so that's, it shouldn't be sensitive to other things. And yet, if I get an ensemble estimate of the linearization of G, this is what I get if I use an ensemble size of 100, 200, and 800. And I think you should look, first, you can sort of see the magnitudes here. The maximum magnitude at the observation location is 0.4. And the true magnitude is 5. So it's off by a factor of 10 in sensitivity. So you would expect it's going to converge a bit slowly. But look at also all the noise around here. So this is one of these things. It could certainly benefit from some kind of localization, but it's just it's weak. Even if you localized it, it wouldn't look anything like it should. Okay. So that's a problem, and the reason is, okay. I should also point out. These two. This is if you go to a really large ensemble size. So the problem is, even if you go to a really large ensemble size, you don't get the correct answer. Okay. So that's because of nonlinearity. So anyway, this is where I'm going to propose this hybrid, which, like I say, it looks a little bit like. So using the chain rule I need these. If I had just written this in terms of the way we would write a normal Gauss-Newton update in terms of prior covariance and the sensitivity of observations to parameters, if I had written it like this, then what I need is these G's and what we used in the ensemble method was just this. I mean, you don't actually always form it this way, but this is the way you can think about it a lot of times. It's just this directly from the ensemble instead of from an adjoint. Instead of from an adjoint, it's coming from the ensemble. But now I'm going to do almost exactly the opposite of what Hung did. I'm going to actually do that chain rule, and I'm going to say, well, I can break that up. There's a part that I really do need the adjoint for, where I would rather not use the adjoint because I don't have an adjoint available and I don't want to spend a lot of time writing an adjoint. So that's this, the derivative of my observations with respect to my model parameters. So that's the derivative of water cut with water saturation with respect to permeability field. Okay, so that's I need the ensemble method for that. But there's this other part, which was the derivative of M with respect to my hyperparameters. And that was trivial. You saw that. That was just this Cholesky decomposition method. So that part I can differentiate trivially. Okay. So that's what I mean by hybrid. And then if I use that in a hybrid filter, I've got some things. So I put in. I'm calling this the one I'm getting analytically. This is what I'm getting from an adjoint. It looks a bit scary. For one thing, it's got this CX out here, which is my prior covariance. And, that sounds like nobody would want to normally form a prior covariance. But if you remember, my prior covariance for Z, which is my big spatial one, is the identity matrix. Okay, nobody minds using the identity matrix. Okay. And my other three hyperparameters are independent. So this is actually a diagonal matrix. So the fact that a huge matrix appears there is almost misleading. It's not actually needed. Okay. And this, oh, I didn't look at the time.
4 minutes, 6.
Yeah, anyway, that's so good. At least I'm glad I went slowly over the part I went over. It's hard to believe I only did 5. Okay, so anyway, these I would have gone over fast. It just shows, I did want to just compare. So now I get this is now the same problem you saw before. This is a prior, this is history matching with a hierarchical model. And they're not perfect. They're not as good as I would hope. So there's one actually didn't history match. And there's some additional problems when you try to history match that these show. You don't need to look a lot of these. There's some additional problems that show up in history matching with long correlation lengths. And it has to do with, now you start getting into problems with local minima, where you actually have a channel appears either on one side or another, and to make it move, it has to go over a region that's less probable. So it's a bit harder to history match, not simply because it's hierarchical, but because it's got some long correlation lengths. Okay, so we also, in addition, I'm not going to show you how the Z evolves, although actually Z was a little bit interesting. But the hyperparameters, they didn't actually converge to what the truth was, which surprised me a bit. And I should look a bit more at that. But and actually my correlation lengths got longer, and I would have thought they might have gotten shorter. Okay, and by the way, okay, so this one is a little bit interesting. This is the hybrid S. Oh, actually, since you've got looking at it on this screen up here, you can't even see the spurious correlations. There are some spurious correlations over here, but they're relatively small. But look, the magnitudes are close to right. So these are now sensitivities without localization. This is simply using a hybrid method. And again, I'm still using the iterative ensemble smoother for the sensitivity of, in this case, sensitivity of my measurement to the model parameter. Okay, so then now a summary. I do think we need to get models that are more forgiving of model imperfections. I mean, we need to use priors. When we use bad priors, what happens is people they stop, they rebuild their model, and it's a long time consuming process. Hierarchical models, I think sometimes what people think of as some different in the petroleum industry, they think they need scenarios. I need to consider short correlation length, long correlation, whatever. Sometimes you can handle that within a continuous parameterization, which makes more sense from a Bayesian. Okay, and so I will say this hybrid method was a lot better at assimilating data in a hierarchical model. It's actually not limited by Gaussian assumption. I didn't make that point very well, but each ensemble member has its own Kalman gain. And since it has its own Kalman gain, it can move in a different direction. So you can actually have a multimodal distribution, which is unusual for an iterative ensemble method. Okay. I will say that my current toy code is quite slow, and that's because I'm actually computing the square root of C. I'm forming and computing the square root of C directly. But to be honest, all you really need is to differentiate the covariance function. So you don't need to you're not differentiating the covariance matrix. You need to differentiate the covariance function. And then there's lots of methods where I could have been faster than this. But I was saying one place where it would have been probably kind of nice here is is to use a form that's naturally sparse. Because if not, I could use something like a convolution product where I don't need the covariance matrix. I just need the product with something else. I could use a more efficient method of doing that. And so that's where it stands right now. Anyway, I don't know if there's even, nope. I think I I timed it perfectly so you couldn't ask questions.
Yeah, it's not really time for questions, but if there is a quick one, maybe it's, okay. Otherwise, I think
Maybe I can ask a quick one.
that's okay.
Yeah, I think you used the original ENR mill. So have you tried this Lemberg version?
No, I just didn't show lambda. For simplicity, I didn't show the.
Because if you use that one, then also you don't have these terms there.
No, I use Lemberg McCoy form.
Okay, thank you again. So the next speaker is Koji Yamamoto.
Online. I need to stop sharing first.
So he's.
Hi, Koji. Can you? Yes.
Hi. Yeah, Luo, can you hear me?
Yes, I can hear you. Can you start sharing your presentation?
Okay. Can you see my presentation?
Yes, we can see it. Sorry, I'm sorry. Yes. Can
Okay.
you put it into the display mode?
Okay.
Presentation mode.
Okay. Can you see?
It's not in the presentation mode, I think. It's not the full screen.
Okay, I will try again. How about it?
No, it's the screen. I think it's not in the presentation mode. If you can click yes there, move a little bit to the right. You see there's an icon on the top menu. Yeah, now you need to move your mouse to the top of no, okay, so I cannot see your mouse. Yeah, I think there's an icon there. Left to the left. Oh, no, you.
Sorry.
I think you. No, that's okay. I think your talk is the last one before lunch, so actually we could have a little bit extra time for you. Yeah, if you can move your mouse to the top, to the very top of a point. Yeah, now to the left. Yes, to the left. Yeah, okay. Oh, you just passed it. Up a little bit. Yeah, and then to the right. No, not this one. Need to be right. Yeah, that's one. Yeah, okay. Yeah, that's one. Does it work?
Yeah, I clicked, but I can see the presentation mode.
Yeah, that's.
Okay, I will try to do another way. Yeah.
You can make it full screen. Can you try that?
Yeah, I made it, but maybe it didn't.
So maybe
work
because
for...
maybe because the display setting, we kind of have had a similar problem on Monday because the display setting. Yeah, click
How
that
about
one.
this?
Nice. Yeah, perfect. Yeah, that's good. Yeah, then please start.
Okay. My name is Koji Yamamoto from JOGMEC. Now the Japanese government and Japanese many organizations are working with gas hydrate. Gas hydrate is a kind of the natural gas. And it is a possible one application of data assimilation technique. So I want to introduce. And this presentation, myself and Hisanao Ouchi, two people will share the presentation. First part, I will talk about what is a gas hydrate and how to produce a methane gas from gas hydrate. And also possible application of data assimilation. And I want to introduce about long-term gas production test in Alaska. And later part, Hisanao will talk about preliminary data assimilation tests. Some example we try using 2D models and future possible 3D models. So I am talking about gas production from naturally occurring gas hydrate. Maybe some of you are not familiar with gas hydrate. It is a solid material containing water and methane, and it is stable under high pressure and low temperature condition. So the geologists believe that huge abundance of the gas hydrate exists in deep water, subsea, or permafrost region. So some countries like as energy poor Japan want to use the gas hydrate for the future energy. And because it is stable under high pressure, by reducing pressure, we can take the gas from gas hydrate. So we believe that this depressurization method should be the most realistic solution in the viewpoint of energy efficiency. And one specific point about this gas hydrate dissociation is it is an endothermic process. A lot of energy is consumed. Already some countries like Japan, China, Canada, United States have done some production tests in gas hydrate from naturally occurring gas hydrate reservoir. But it is those tests are relatively short term, just a few weeks or a few months. So we want to do the long-term production test. One problem is a lot of uncertainty in the reservoir characters. Gas hydrate production process is thermo-chemo-hydrocoupled. It is a little bit more complex than the usual conventional gas and oil reservoirs. In the reservoir study of oil and gas reservoir, usually we are trying to solve the equation of the transport of fluid in the porous media by using Darcy's laws and mass conservation. But in the case of gas hydrate, we need to consider about the thermal heat transport using Fourier's laws and also energy conservation. And also, we need to consider about the kinetic equation of gas hydrate dissociation process. And another interesting point is, in the case of a gas hydrate, permeability is not a constant because gas hydrate dissociation causes a change of gas, permeability. So permeability is one of the variable. But because the gas hydrate dissociation is an endothermic process, we can detect the dissociation of the gas hydrate by taking the temperature data. So when we produce a gas from gas hydrate reservoir, of course we can take data of the flow rate of gas and water, and also we can take a pressure and temperature data from the sensors. And using those data, we can make the data assimilation. And we need to take data information about the permeability and gas hydrate saturations. Initial data of those permeability and gas hydrate saturation can be taken from seismic log and core data, so we can make initial ensembles. In the case of 2017 Nankai Trough gas hydrate test in Japan, we drilled two producer wells, P3 and P2, and two monitoring wells, MT3 and MT2. And all of the wells, temperature and pressure sensors were deployed. And by using those data, we could get the information of gas hydrate dissociation in the 3D space. So process of assimilation is not far different from the usual oil and gas reservoir. Initial reservoir model ensemble can be made from the seismic or the core data. And one specific point is we need a special numerical simulation model using a thermocoupled model. And actual measurement of water, gas, and rate and pressure temperature data will be used for the assimilation. We have tried ensemble Kalman filter and ensemble smoother for the assimilation. And we have some methanol hydrate specific features. One is, of course, it is a THC, thermochemical hydrocoupled, so more variables than usual reservoir modeling. And expansion of gas hydrate dissociation front means that gas hydrate original around the gas hydrate dissociation start from the production well, and it will be expanding. And each variables, like the temperature and hydrate saturation, has a strong correlation because the gas hydrate saturation reduction causes the temperature drop. Of course, gas hydrate saturation and effective permeability has some relationships, but those relationships are linear. And we want to do some long-term test. So now the Japan and the US government are making a collaboration project. And it is planned to start in the next winter, next summer, maybe coming in a few months. Already we have drilled a lot of wells, and we have drilled one well for the exploration and take the data. Also seismic data have been taken, and we are drilling some monitoring wells. And by using data from producer well and monitoring wells, we will try to do the data simulation. This test will be planned to continue for 1 year. So during this 1 year project, we will try to apply the data simulation methods and evaluate the effectiveness of them. Already we have done some tests of simulation. So those results will be presented by my colleague Hisanao. So I stop the sharing.
Okay.
And Hisanao, please.
Okay. Can you hear me?
Yes.
Okay. Then from now on, my name is Hisanao. From now on, I would like to explain the rest of the presentation material. Can you see my screen as presentation mode?
Yes, yes.
Oh, okay. Then I would like to explain the preliminary data simulation test for the long-term production test in Alaska. This is a kind of numerical experiment to investigate how accurately the reservoir parameter could be estimated through data simulation. Then let me start from introduction. At first, I'd like to explain the simulator and data simulation framework utilized in this study. We utilized MH21 hydrates, which is thermohydrochemical and multi-phase reservoir simulator developed for the prediction of gas production from the methane hydrate reservoir under MH21 Research Consortium in Japan. And also we utilized PDAF developed by Computing Center of the Alfred Wegener Institute as data simulation framework. Then next, I would like to explain the data simulation algorithm utilized in this study. Data simulation algorithm can be categorized into two types, filter types, in which observation data in each time step is assimilated sequentially. And another one is smoother type, in which observation data of all the time steps are assimilated at the same time. And when comparing these two methods, filter type allows to modify physical parameters discontinuously in each step. So it is considered to be suitable for highly nonlinear system. But in the case of methane hydrate simulation, unfortunately, I cannot explain the detail. Discontinuous physical parameter changes caused by data simulation sometimes could lead to catastrophic calculation instability. And on the other hand, in the case of smoother, it modified parameters only at the initial condition so as to match the observation data of all the time steps. So it is relatively difficult to follow sudden physical condition change down filter, but and calculation instabilities caused by discontinuous physical parameter modification, such as filter, never happen. And in addition, by iteratively applying the smoother types of method, the accuracy of the parameter estimation could be improved. So in this study, we decided to use smoother types of method. Iterative and sample smoother was selected. Then next, I would like to explain what kind of observation data will be taken in the production test in Alaska. In addition to the producer, 2 observation wells will be drilled in the test. Then in the producer, during 1 year production term of depressurization, and gas and water production rate will be observed. And also in the observation wells, GDW and STW, reservoir pressure inside the methane hydrate zone will be observed at the 2 fixed points, shallower part and deeper part in methane hydrate zone. And also reservoir temperature will be observed along with the observation wells by using DTS, distributed temperature sensing. Then next, I would like to explain what kind of simulation model could be utilized for the data assimilation in the production test in Alaska. Actually, there is a precise 3D reservoir model for the long-term production test in which fault and layer thickness change are considered, and also lateral heterogeneity of the reservoir properties are considered. However, since methane hydrate simulation requires very small grid blocks in order to keep the calculation accuracy, after applying the local grid refinement, the number of grid cells exceeds 5 million. Then as a result, required memory size became 20 gigabytes per single simulation. And also calculation time is about 5 to 10 days per single case for 1 year prediction. Practically, it is not applicable to the data simulation where more than 100 simultaneous simulations runs are required. A much faster model than 3D model is required. Then the primary candidate is the 2D radial model. However, 2D radial model have huge model representation errors. In other words, it cannot express the important feature of this field, such as fault and lateral heterogeneity of the reservoir properties. So the question is, are they really applicable to the reservoir parameter estimation through data simulation? Then this question needs to be evaluated. And let's move on to the preliminary data simulation test by 2D radial model. As I said in the introduction section, the amount of observation data is limited, only coming from 1 producer plus 2 observation wells. And also, due to the calculation speed limitation, we need to use 2D radial model, which has huge representation errors. So the question is how accurately the reservoir parameter could be estimated through data simulation under these 2 conditions. Then in order to investigate this question, we conducted 2 cases of preliminary data simulation tests by using 2D radial model. In those tests, we extracted hypothetical observation data from the simulation result of 2 different types of reservoir simulation model, 2D radius model, and 3D homogeneous model. And in case 1, hypothetical observation data was taken from the 2D radial model. So 2D result could be perfectly reproduced by 2D model. There is no representation error in this case. The primary objective of this case is to investigate how accurately reservoir parameter could be estimated under limited observation data condition. Then in the next step, we extracted the hypothetical observation data from the laterally homogeneous 3D model. In this case, since 3D model result cannot be perfectly reproduced by 2D radial model. And clearly there is certain degree of model representation error. The objective of this case is to investigate how accurately reservoir parameter could be estimated through data simulation under the condition where huge model representation error exists. Then in these two cases, we estimated absolute permeability and permeability reduction index of each layer through data simulation using iterative ensemble smoother. And this is the parameter distribution of estimated parameter of each ensembles. From left figure, absolute permeability distribution in horizontal direction and absolute permeability distribution in vertical direction and permeability reduction index in horizontal direction and vertical direction. The blue line shows the parameter distribution of initial ensembles, and red line shows the parameter distribution of difference model. Then as you see in this figure, the parameter range of initial ensembles are different, depth by depth. The reason is the uncertainty of the well-log interpretation are different, depth by depth. Let me explain more about this. There are 3 different well-log interpretations in this target reservoir. Let's say minimum interpretation, most likely interpretation, and maximum interpretation. Then each ensemble distribution of each ensemble member is generated by interpolating these well-log interpretations in order to keep the parameter trend of well-log interpretation. Then this difference between minimum and maximums are different depth by depth. In other words, the uncertainty of well-log interpretation is different depth by depth. So the distribution of initial ensembles are different depth by depth. One more point I would like to say here is, in the methane hydrate reservoir, effective permeability is expressed as the function of absolute permeability times 1 minus hydrate saturation followed by permeability reduction index. Then in this study, we just estimated these 2 parameters. And regarding the methane hydrate saturation, we just used the most likely well-log interpretation value. Again, let me explain case 1. And first, I'd like to explain the case 1 settings for the data simulation. In this case, as I said in the previous slide, we extracted the hypothetical observation data from the reference model in which most well-log interpretation properties are utilized. Then this result are simulated by 2D radial model in which grid frame is exactly same as the reference model. So there is no model representation error in this case. And as observation data for data simulation, we utilize these 3 data: and cumulative gas water production in the production well and pressure temperature change at the observation well location. And we assume that those data will be taken at every 30 days until 240 days after production begins. Again, this is the result of the case 1 regarding observation data of the production well. And left figure shows gas rate and right figure shows the water rate. Okay. Then blue line shows the simulation result of the initial ensemble members, and the orange line shows the simulation result after applying the data simulation. Okay, then as you see in this figure, both in gas rate and water rate, and the simulation result after data simulation closely approaches to the reference model result. And this is the result regarding the observation well location, pressure temperature distribution after 240 days. Then as you see in this figure, simulation results of the ensemble member after data simulation closely matches to the reference model result like this way, both in temperature and pressure. Then this is the result of estimated parameter through data simulation. Then as you see in this figure, at least in the methane hydrate zone, estimated parameter through data simulation very well matches the reference model parameter distribution like this way. So this result shows that by using the observation data set, which will be taken in the production test, we could estimate the parameter distribution of the target reservoir. Then let's move on to the case 2. In this case, hypothetical observation data was taken from the 3D homogeneous model, in which most likely well-log interpretation value is applied to each layer. Then in this case, as observation data for data simulation, we utilized 2 data, cumulative gas water production of the production well and pressure temperature change at the nearest observation well. In this case, we didn't include STW observation data because if we include this data, our preliminary study showed that the accuracy of parameter estimation became worse. So in the final trial, we didn't include STW data. Then data acquisition timing is exactly same as the case 1. And this is the result of case 2 regarding observation data at the production well. As you see in this figure, same as the case 1, after applying the data simulation and the simulation result of each ensemble members and closely approaches to the reference model result. Then also in the case of pressure and temperature change at the GDW well location, we can see that the simulation result after applying data simulation very well match the reference model result like this way. And this is the estimated parameters after applying the data simulation. As you see in this figure, although in the lower part of the methane hydrate zone, we could see the slightly estimation difference, but in overall estimated reservoir parameters through data simulation very well matches the reference model parameter distribution. Then in conclusion, we confirm that the observation data taken from the 2 reference model could be well reproduced by the data simulation of the 2D radial model. And also reservoir properties of the reference model could be estimated with a certain degree of accuracy. And these results suggest that the reservoir property could be estimated with a certain degree of accuracy through data simulation using 2D radial model in the actual long-term production test Alaska. And then finally, I would like to briefly explain the future study plan using 3D model. In the preliminary study, we utilized 2D radial model, but in this study, we would like to use the upscale 3D model, which calculation speed is much faster than the original fine model. Then as a next step, we are planning to investigate how accurately the following properties of the reference 3D model could be estimated by data assimilation of these upscaled 3D model. Horizontal distribution of represented relative properties such as hydrate saturation, heterogeneity, and absolute permeability heterogeneity in lateral direction, and fault transmissibility near the production well. Then, if this system successfully works, data simulation using the upscaled 3D model could be possible in the actual long-term production test in Alaska. Thank you very much for listening. That's it. Should I stop sharing my screen?
No, not right now. Maybe you will get the questions. So
okay.
That after. Maybe I can start with a question. So I'm not quite sure. Is since so far you for your homogeneous models, how many number of parameters do you have?
Ensemble number of ensemble members, you asked?
Yeah,
100.
100, right?
100, yes.
Is that the ensemble member or the number of unknown parameters?
Okay. Number of parameter is just 2 absolute permeability, but the actual number of unknown is the 2 parameter times number of grid layers.
Yeah, that I see, because it's homogeneous. So by that way, you have a kind of a reduced number of unknown parameters.
Yeah.
And if you go to heterogeneous models, then maybe you will end up with more unknown parameters.
Yes, actually, we tried heterogeneous case. Unfortunately, I don't have enough time to explain these cases, but at least if we use the heterogeneous model as hypothetical observation data, let me see this result. Yeah, we could get a very good matching, and at least in the location, production well location, we could estimate the reservoir parameters very well. In this case, in addition to these 2 parameters, we selected methane hydroxide saturation distribution of all the grid blocks as unknown.
Yeah, okay. I ask the reason is that because I guess in this case, you possibly have a larger number of observations than the number of parameters. So this kind of problem is sometimes easier to solve. And you go to heterogeneous models, then you tend to have a larger number of unknown parameters than your observations. So actually related to this comment, I'm wondering, do you plan to use any seismic data for reservoir characterization?
Actually, our methane hydrate distribution in the heterogeneous model is based on the seismic data.
Yeah. Okay. But I mean, my question is that in the future, do you have any plan to use seismic data for reservoir characterization in a way?
You mean 4D seismic?
Yeah, maybe 4D or 3D. I guess in that, you have more data to constrain your reservoir model, I guess.
Yes, but when we construct the 3D reservoir model, of course, we utilize the seismic data result. For example, in the high-speed region, we could expect the high methane hydrate saturation, and the low-speed region, we expect that the relatively low methane hydrate saturation. That kind of information is already used in our 3D model.
Yeah, okay. It's actually used that to generate the initial ensemble of reservoir models. But you didn't use that in his matching. But of course, you can consider that.
Yeah.
In the case of our project, we will try to do the 4D seismic using a VSP. But a problem is we can take the seismic data at just the beginning and the end of the production test. So those data can be used to know the final situation, but we cannot use for the data assimilation.
Yeah, I do understand. Yeah, it's actually sensible because it's an initial study and it takes time actually to make it more successful. Yeah.
Yes, that is the
Sorry?
Sorry, I cannot hear.
Yeah, I cannot hear.
I just wanted to say thank you very much for this very good presentation. Unfortunately, our time is up, so we don't have time for more questions, but I hope to see you again next time. Maybe you have more results using the data from this Alaska test. So I hope to see you again.
Yeah, thank you very
I
much.
hope, yeah, I want to see you face to face next time.
Yeah, that would be good. That would be good.
Yes, very nice. Yes, thank you. I sent it.
Thank you.
Yeah, you can put it here. I will ask them to lock the door. Can I ask, Dinesh, can you take your poster because I want to write some information? Yes, yes. You want to upload? You want to use your computer or?
I can just use this.
Yeah, that'd be good. Yes. That's the information. Don't try to say anything before, before lunch. You can just go for lunch. You don't have to wait. So then the boat time. The boat meets at 4:15. I hope you guys. Hopefully you can show up 10 minutes before the departure. Okay. And yeah. Okay. Let me use microphone. Sorry, I didn't expect you guys still stay in this room, but since you are still here, I can say something. So the vote will meet at 4:15, okay? And then I hope you guys can show up roughly 10 minutes before the departure time, just in case you have any emergency issue to handle, okay? And we ordered some food for you guys to carry before boarding. So please take one of that per person after workshop. So I think it is maybe available after workshop between 2:30 and 3 or something. You need to go to either the reception desk or the bar. I don't know exactly where it would be. Okay. Yes. Okay. Thanks for that.
Yeah. Okay. Good.
Yeah.
Can we, before you go to the next presentation,
yeah,
can we just put up our title because we have the task of taking a picture from the workshop?
You can.
We technically do like slump squat.
Yeah, just send is a slide or something.
You already have the slides. You got them on the.
Oh, okay. It's the same presentation, right? Yeah. Sure. I saw that you have a separate. I'm sorry for that. I saw you have a separate. Yeah.
And just like full screen.
I need to do something else first. Yeah. Before making full screen, I need to do something else first. So I will do that afterward. Yes. Yeah, if you want. But I cannot help at the moment. If I'd ask this lady or gentleman or yeah.
can we trust more? Now we have to have choice.
Oh, it's just you criticize the graph.
I didn't criticize.
It is binary. It's binary, so it's very easy.
Yeah, okay. Then it's
Sorry, what did you say? Did you say anything? Oh, I'm sorry. I and Mira, can I ask you for a favor? I mean, you are Florian. Yeah. Have you uploaded your?
I was in the process of doing it.
Oh, yeah. Have you put it in the?
I have it on the USB stick, but not on your computer.
Okay. Yeah. I can. Yeah.
No, it's on the stick.
Oh, it's on the stick. I'm sorry. Yeah, I found yours, but I didn't check. I didn't check. I'm sorry. Yes. This one? Yes. Yeah, that's okay.
I hope you have PowerPoint here.
Yeah, you're talking before me, so maybe okay. I put mine here, so fine. Yeah. Then we have three yes, on-site speakers. Let's say that. Yeah. I will. Yes, I can. Oh, slide. Yes. I'm sorry. Yes, I forgot that. Let me say.
Tested this? Okay, I'll give you a wait. Yes. I think almost everyone is back. Sheldon, can you check if people are still outside? Thanks. So yeah, this is our final session. We have 3 speakers left, and the next speaker is Nina from NTNU. The topic is on Bayesian seismic rock physics inversion using localized ensemble-based approach. Please go ahead.
Okay, do you hear me? I think this should
be working. I'll just have to carry it. Don't have any pockets. Hello everyone. My name is Mia Spanish, and I'm a PhD at NTNU in Germany. And today I will be talking about, as Michael said, about Bayesian seismic rock physics inversion using a localized sample-based approach. And this is going to be mainly about application to the Alpine field. And this is done in collaboration with my supervisor, UITIC, and Pet Assets. Okay. All right, we'll see. So I will be telling briefly about the goals of this study. Then I will introduce the case of the Alpine field. I will let you know more about the likelihood and the black box of the geophysical forward model. Then I will proceed with saying a bit more about how we structure our prior model, about some results, and then I will finish with some concluding remarks and further work. So what we wish to do is to invert for the continuous reservoir parameters, which are oil and gas saturation, as well as the clay content. We perform 2.5D inversion on the top reservoir using localized ensemble methods. Then we also condition on the available seismic and well log data, and we wish to provide more realistic uncertainty quantification by accounting for the cementation and the geology of the area where the Alpine field is. Back. Okay, so the Alpine field is situated in the North Sea, very close to the border with the British waters, and I believe Bergen is here, something like that. And as I mentioned, our main interest is on the top reservoir. As you can see here, these are the travel times of the top reservoir. We have the grid is in crossline and inline coordinates, and every inline and crossline has a corresponding travel time. So each location is at a different depth. Hence why we say that we're essentially doing this 2.5D inversion, because we want to include this depth dependence in our model. And at each location, we also have AVO data, which is the seismic data that we use. It is the zero offset coefficient and the gradient, which I will tell more about. So I don't know, I would assume, okay, I would assume that quite a few of you are familiar with AVO data, and then some are maybe not, but it stands for amplitude versus offset. And basically amplitude variation is dependent on physical properties at the interface. So in an oversimplified words, we shoot some waves down from the sea surface, for example, and they reflect from different interfaces. And they also transmit as well. And after some processing of the data, we do a linear fit of changes in amplitude versus some of the incidence angles, and then we extract the intercept and the gradients at the top reservoir. This is not something I've done. I have gotten my data, luckily, from people that are way more knowledgeable about this. But essentially, to obtain this with a model, one needs to use Lockridge equations, where the input is the elastic parameters, or use an approximation, like, for example, the Schulze approximation that I'm using. All right, so this is the data. This is the zero offset or the intercept and the gradient. And this is the depth sort of map of the top reservoir. The 4 circles indicate the 4 wells that we have data available from, and the red indicates that at the top reservoir in that well we have gas, and green indicates that we have oil. So this is something that we will be incorporating into our prior model. This is the well logs from the 4 wells. And essentially what we see here is that in 2 of the wells, we have quite clear differentiations between the different fluids, but at the other 2, not so much. And this also corresponds to the increased clay content at those regions. So this is also motivates why we are inverting for continuous parameters and not doing classification, but it also motivates the choice of the rock physics models that we use later in our forward model. All right. Here is sort of a diagram of how this works. So we have this depth dependence included in our Gaussian random fields that we use to generate realizations of saturations and the clay content. Then we have porosity, which is not a stochastic parameter itself, but is sort of indirectly so because it is dependent on the clay content. And then we have this black box section that I will zoom in a moment, where all these rock physics and geophysics models are put together to give us our simulated data. Also, I should probably mention that in this Shui approximation, where we finally obtain the intercept and the gradients, as I've shown before, we need elastic parameters above the interface and below the interface. And to obtain the parameters above the interface, or so-called caprock, we estimate these from the well logs, and they are constant over the field. Now, I was very enthusiastic to show my horrible illustration skills, and I made this to try to give you some sort of intuition and idea about what is going on in this black box forward model. Without including way too many equations, because these equations will probably take up as many slides as I already have. But essentially, let me try to explain this. So we have our depth dependence, we have our clay content and porosity and cementation depth. So this cementation depth is quite important here in the model because it tells us whether we use one model or the other model. So first we have some different types of rock material. We have maybe some quartz or clay, and then we either have these unconsolidated sands, or we have some of the cementation that has been appearing on the outer side of the grains. And whether we use one model or the other depends on where the cementation depth is set at. So then, depending on which model or which, I guess, section of the depth we're in, we obtain the dry bulk and shear modulus, and are in the stage where we have this rock matrix, and we want to include our saturations in this. So we have our mixed fluid saturation model, and then we use do gas fluid substitution to fill this pore space. And by that, we obtain these elastic parameters, which are P wave, shear wave, velocities, and density. And then finally, through the Shui approximation, we get our simulated data. Yes, if you have any questions, just shoot right away. Then we want to cast this or set this into the Bayesian framework with the prior model. Our age of X is a bit more complicated than just this, but this is our observation model with a Gaussian error. So it's a nonlinear model because it depends on depth, it depends on this cementation depth point, and we actually aren't so sure about, and porosity. And our covariance matrix is block diagonal, 2 times 2, with some slight negative correlation between the gradient and the intercept. So a bit more about the prior model. So we wish to, since we have all this well log data, we wanted to make prior a bit more informed, to give it a bit better starting point, because it is known, I would say, in the geophysical community of people who do work with reservoirs, that we find usually gas at in the more shallow sections of the top reservoir, while the oil is normally appearing underneath it, and then in the most deep parts of the top reservoir, we mostly have brine or water. So this is also something that we have as a goal to incorporate in our prior, and our prior is estimated from the well logs. as a Gaussian process, you can see here with the uncertainty, and to generate the prior, we use Gaussian spatial correlation function, and due to the high dimensionality, we use the FFT routine to generate the ensembles. But then after we have generated our ensembles, we perform a logistic transformation of the saturations because we cannot deal with the values that are on the real line, and we want them to be between 0 and 1, because we want the saturation to sum up to 1 at each of the points. Now some plots finally. So in each of the slides, when I show some of the figures, I will be including this depth of the field, because I think it's interesting to see all of the results with respect to the depths, especially since the saturations are connected to how deep we are at, amount of saturations. So here we see the prior mean of the gas organizations of the gas saturations, oil, and then the brine, and the associated uncertainties, which is the width percentile. So we generate for all of the results 100 realizations, and here we take we look at the width between the 10s and 90s ensemble as a measure of uncertainty, and also clay content as well, as you can see here. So we capture this as intended, that in the a bit more shallow regions, we have a bit higher saturations of gas, and then in the mid ones, I think this ran out of battery. Yes.
Sorry. Yeah, but my copy.
Okay, does you hear me? Okay. All right. But then, since we also know, as I showed in one of the previous figures, that at certain points we know whether we have oil or just gas or nothing, we wish to condition on this before we do our data assimilation. So we use 3 out of the 4 wells, as the 4th one is a bit on the edge of the main, just due to simplicity. And as you can see, after the update, we have way higher saturations in the regions where the well is. So the white dots indicate the locations of the wells with the corresponding saturations. And we also see that naturally the uncertainty has been updated as well. I also wanted to illustrate this. I wanted to illustrate this update as well here with this. I don't know how familiar with ternary plots, but basically at each point your the saturations are supposed to sum up to 1. And we see this here is for only 1 inline and crossline location, as marked on the figure, for the 100 realizations. So you see the updates, and this is at the edge of this area where the saturation of the gas has increased due to the update. Here is the simulated seismic data. So after we have run this conditioned priors through our black box model, so you see that some regions here that are supposed to be more shallow are a bit more different in color than the rest of the field, and this is due to these 2 different rock physics models that we're using, depending on whether we have unconsolidated sands or if we have cemented ones. And over here we have a cross plot of ADO data. The black is the real data, and the colorful clouds are supposed to be different realizations. So we wanted to see how well we cover the real data with our prior model, and we see that we're doing quite okay. We're not managing to capture this tail over here, but we think it's not that alarming, as it is most probably the reflections from the shale rich regions that are mostly filled with brine. We approximate our posterior, and we use for this localized ensemble transform common filter that most of you have talked about a lot. And I will just say that our localization is rather simple. We divide our grid into squares, and we have a bigger square that is observation square that we use for updating the smaller parameter one. And then we just keep going like that until we have updated the whole space. We also compare it to the localized EnKF, and here we, for each patch, so for each of these observations and parameter pair patches, we perform the J number of iterations, and then we keep going for each of the patches. The data simulation window here corresponds to the observation patch, so we don't divide the observations any further than that. And these were just the algorithms of the method. So our reference case is where we have observation patch of size 16 × 16 and parameter patch of size 6 × 6. And the segmentation depth is at 2,110 meters, I think, approximately. So the results I will be showing will be showing when we what happens when we vary the observation patch, when we vary the parameter patch, when we try different segmentation depths, and finally when we used localized derivative ensemble common. So here we see that a lot of the structure, if you recall, that have been here around this updated area have disappeared, but that when it comes to the oil saturations, we actually have some sections here that are indicating a higher saturation of the oil. And around the edges of these areas around the wells, we see that uncertainty is much higher than in some other regions. And would say it's also a good sign that in the deeper sections of the field, as you can see here, there are no updates, as we are most certainly sure that that's what we have there is right. We also have 2 remaining wells, so it will be interesting to see once we get them whether our model is how our model is doing there. But essentially, it is a bit few data points to do any more validation. So we are thinking about using some validation with the seismic data itself. Then we decreased the observation patch, and there is a slight update, but not so much. I guess in some sections the uncertainty increases, but not much more. Then we increase the observation patch, and you can see that there are not as many details naturally in the oil saturation, but we also something we don't condition or we don't do a conditioning step for the clay content because it has quite high uncertainty. So it is something that we haven't really figured out how to implement in a good way. And we see that the uncertainty here is also actually quite low. Then this, so this is then for the segmentation depth of 2,110 meters. And then when we increase the depth, meaning that we use this unconsolidated sun model in a larger area, we get this. And we see that the sections are increasing as the segmentation depth increases, meaning that probably in the unconsolidated sands is much more, the saturation also increases, and then the uncertainty naturally follows. So this it shows that this segmentation depth is a quite important part of the forward model, and perhaps something that we will include in the something that we will attempt to estimate in the future. Because at the moment it's more just as a from the knowledge of the field that we were trying to approximately set that segmentation depth. And then finally, for the EnKF, we just run a few iterations because there is not actually much of a difference. But the interesting thing here is that the uncertainty in the clay content seems to be much higher in while using the localized EnKF compared to the LATKF. While the other two don't change much, and actually the uncertainty in the oil and gas saturations decrease a bit. Yes. So I would like to conclude with what we've done. So we performed a 2.5D inversion of the reservoir parameters, and we have been focusing on the saturations of oil and gas, as well as the clay content. We have used localized ensemble methods to assimilate available seismic data. And in the future, as I already mentioned, we will try to validate our results using some of the seismic data, and we wish to perform even more sensitivity analysis. And as you see, it is quite important what is in the forward model. So there's definitely more work to be done there. And essentially, these models that we're using there are just an approximation of what is actually going on. So let's see how that goes. And also conditioning on the, of course, the remaining well load data. That's all I had. Thank you.
Well, timing, almost exactly 22 minutes. So I have 8 minutes for question.
Just to make sure, is this a real field case study or is
This is the real data that we have of the fields.
But I mean, when you using this localized, I think somehow similar to local analysis. You just do this analysis within certain regions. But do you see any effect of non-local observations? Because I mean, I can imagine that if you just do destination using the data in localized region to update the say parameters within this region. But what if I train the data beyond your selected region, still have some impact on these parameters?
That could happen. Yes.
Yeah.
So it's definitely something that that is not easy to determine.
Yeah.
Especially if the channels are. So this is where we collaborated with Offset, and then he has quite a lot of knowledge about this about the application itself. So it could be that there are some channels that have influence, but at the moment we, I guess, don't assume that is the case.
But what kind of the criteria that you use to select the shape and the size of a local region? It's just rectangular or something. Yeah, okay. I know.
Yeah, good presentation. Based on the results, what do you think is the current, because you're saying there's further improvement in the forward models, what do you think are the, based on the results shown here in your opinion, what are the key processes you think need to be added or improved in the model?
So we definitely need to think more about the cementation depths and how we're going to, whether we're going to include that into estimation or not, because it obviously has a lot of influence. But as you've seen already, the conditional update also has a lot of influence to begin with. And definitely the clay content is another point where we haven't tried all the different models, because at the moment I believe we have using a laminated clay model and in there, and there are some others that we could be trying to represent the geology even better and to get a better estimate of how the clay content is across the field.
Patrick. I don't quite understand all about. I don't know what a 2D a 2.5D model is. So you don't have to stop and explain that yet. But I was wondering how when you started with conditioning to saturation measure, observations at 3 points, for example, 3 wells, and then you showed your prior mean after that. Okay. So how is the prior mean established after the observation at a point? Is there a correlation link assumed, or does it have to do with the depth structure?
So it has the prior mean itself is connected to the depth. So as I've shown in one of the previous plots, it's so I guess I will start answering your question first about why is it 2.5 feet. That's okay.
Okay.
It's because we have this 2D slice, which is the top reservoir, but at each point we know the depth of each point, and that depth is included through the prior. So we have depth dependence, but it's only on this one slice that we're modeling. Hence why it's 2.5 feet, if that makes sense. And then in the prior mean that we estimate through the well log, through that we include this depth dependence. And then after that, we do this additional conditioning on those 3 points where we have just an assumed correlation. Yes.
Any other questions? If not, I'm gonna ask one last. Anyone? No? Okay. So I guess my last question is, do you think in your validation metric, is there something related to exact pinpointing the location of these features? Will that change the performance of for example, the analysis or the prediction drastically? So if you have slight shift in the feature location, will that impact the result a lot?
Slight shift in the
you don't have the exact same location of these lines or these the exact location of these values.
No, I'm not sure. I haven't.
You have okay. The follow up.
Yeah, I take advantage of the 2 minutes to ask a question to you and to the community because I'm quite new and I was wondering why there is always use a pixel discretization of the reservoir instead of, for example, a Fourier modes discretization of the properties. It's not just for anyone.
So Francesco's question was about why do we always use the Eulerian grid for such an application for model representation?
Well, I mean, our one thing is our reservoir models are just discretized. I don't know, there's not so much maybe here, but they're discretized models of, let's say, from porous media for flow. And for this, all of our solutions are on this grid where the properties are defined. It's fairly straightforward in this case to use. I mean, even though I say that when it's discretized, some people then do wavelet transforms and solve, for example, a different set of parameters. But often there's no real advantage that I know of.
Okay, yeah, because the only way that would justify would be an advantage, and wavelet are quite related to real modes. Okay, thank you.
Okay, very well. I think it's time to move on. Thanks, Nina, again for the nice presentation.
I should also, I guess sometimes, especially mathematicians like to switch to a Henry load expansion for the primitive.
Also, because of the issue of turbulence, higher order methods are the only way to deal with the problems. Natural to do something where species of freedom describe the characteristics.
Okay, our next talk will be given by Florian. Let you introduce the title of the talk.
Yeah, thank you. I will talk about handling sparse observations, and I would like to talk, start the talk. Here's the pointer. with a scenario that makes us better understand when we come into an application where very sparse observations occur. So let me start with the case which happened yesterday, more or less. Francesco took a swim in the fjord right next to the hotel. Luckily, he can swim and comes back. But imagine, oh, wrong way. He faints and he's driven passively without swimming and attracted into the ocean. Then classically, the search and rescue area starts. Normally, we talk about disabled boats, but it was just too tempting to begin my talk with your example. Sorry, Francesco. During these search and rescue operations, we would like to define a search area where we expect him or the boat, which represents the drift together with the uncertainty. During these operations, we collect data, in-situ data from buoys, which give us information about the currents. But we have only very, very few of these buoys out in the ocean, which cannot give us the information. So the key assumption here is always that the observations are super sparse. Nevertheless, we want to use data assimilation techniques which handle these very sparse observations in a reasonable way to reduce the uncertainty and give better forecasts. And all this together has to happen very fast, because we don't want to wait for supercomputers to give you a forecast where you are, but we want to regularly update our forecasts and rerun the entire forecast. So I will structure my talk in the following way: that I would start with one simplified ocean model, which I will consider to the rest out of the talk, introduce two data assimilation techniques. One is a modified LTKF, and the second one is a reminder about the implicit equal weight, which are then later on compared on a benchmark case by assessing and evaluating a set of skill scores. Classical ocean forecasting involves heavy computer models modeling the complex physics of the ocean, where the simulation takes several hours. But we take a complementary approach. We use simplified models, which only model the physics which are relevant for a short-term forecast, and still inherit some properties from the full forecast, from the operational forecast by initial conditions or boundary conditions. This enables us then to run really bigger samples than usual, meaning we traded some of the physical complexity in favor for more statistical explanatory power. The ocean model we consider in here is the rotational shallow water equation, meaning the shallow water equation on a rotational frame of reference like the Earth is. To get there from the Reynolds average Navier-Stokes, we make some hard assumptions. First, we have to integrate all our quantities over the water column, ending up with a 2D model, which is only barotropic. It models, given some, is the pointer? Yeah. From some equilibrium sea surface elevation, it models the derivation denoted by eta and the velocity u in x direction and v in y direction, such that in this formulation, in this conserved formulation, the value of eta, the momenta hu and hv are conserved. We are in a hyperbolic conservation setting of hyperbolic conservation law, which can be efficiently be solved by parallelized numerical schemes, like some central upwind finite volume method. This allows us to have a very fast model. So we also want to now to have also very fast data assimilation models. The first data assimilation, first, to get back to data assimilation, let me introduce some common notation. It's more or less the notation we have seen the last days. I denote the state by xn, collecting all eta, hu, and hy over all grid points, which is very high dimensional in an ocean model. The model itself, the shallow water model, is now encapsulated in the model operator M by under addition of some small or rather small model error, Gaussian model error with some covariant matrix Q. The observation model, this is exactly tries to model the observation which we have from the buoys. So we have some operator H which picks observations from a few grid cell locations, taking into account some representation error denoted by epsilon. And the key assumption is this is much, much smaller than the full state vector. And our goal is to assess the posterior distribution by ensemble methods where I use small e to index the ensemble members. The first method we came up with when we tried to solve this was the LTKF, because the LTKF is successfully used in weather forecasting. It's based on the ETKF linear transform linear data simulation method, the ensemble transform Palmer filter, but this EnKF suffers from spurious correlations when we use small example sizes, and the classical strategy to counteract this localization, which comes quite naturally when we look onto the ocean. The paradigm which Hunt uses is, so to say, the analysis of a certain point in space is only influenced by the observations around. We have seen this several times before, but now our observations are so sparse that we want to utilize this fact in some way. And that's why we just turn around the point of view and say a certain observation only influences the analysis in its vicinity. So far, so good. And now we want to benefit computationally from this. Therefore, we do like we have seen before, domain localization. We cut out neighboring regions next to the observation sites, which are in this little illustration are these black dots. And we cut out local regions around them, given some localization radius. And we organize the observation into batches that we say within a batch, the observations are independent, where we say they are independent if they don't overlap the regions around an observation. Ending up in this simple example with two batches, we calculate the EnKF locally and process the observation batches serially. But let's take a closer look on how we process them, because we somehow turned around our point of view before. Given this forecast from the full model on the full domain, and given that we have calculated the LHKF in these local blue domains from the slide before, so we have an LHKF analysis here and here, we construct again our posterior by weighting them quite roughly. We use a weighting kernel, which is 1 at the observation site and decays when we go further away from the observation sites. The classical choice is now the Gasparin-Cohen function, or Gasparin-Cohen kernel. And then we weight our EnKF analysis with the forecast. This was now for the blue observation areas. Now we go to the red ones. Now the forecast can be influenced by the previously processed observations, but we do basically the same for the next observation, for the next batch of observations. We construct these local observation kernels and weight it with the ETKF forecast and the previous with ETKF analysis and with the forecast. Yep,
I'm just not quite clear. Am I seeing the classical EnKF here or modification?
It's a little modification. In the classic EnKF, you get along without this without this weighting.
I didn't quite catch the details, but
okay. In the classic EnKF, you weight your observations with the kernel, with some weighting function. And here we wait after doing the EnKF. This allows us to do less iterations. So in the classic EnKF, we have to do for every local domain, which is predefined, one update. And here we do only as many updates as we have observations. And in our case, this is normally like 2 magnitudes smaller. So it's close, just saving some computation costs. But what we also can include in this case now is we can utilize it for inflation. We have these weighting kernels, and we have observed when we stress test is really like having a 500 by 300 grid and only having 10 observation sites, that we then get overfitting behavior around the observations, which we want to counteract with inflation to keep more spread in the analysis. And this is then done by simply introducing a parameter in front of these Gasparian cone kernels to reduce the influence of the analysis. For 0, this is meaning no analysis, pure Monte Carlo simulation. And for 1, we would be back into the classic scheme which I presented before. Therewith, we have one method we want to compare later on. And the second one is implicit weight, which I just will recall briefly. While the classical particle filter, which were not so much topic of the last days, reweight, and I know there exists many different versions and tweaks to resample the particle, but we will not look into them. We will look into the implicit weight particle filter, which uses actively the covariance matrix to pull the observations towards the to pull the sample towards the observation. This setup has shown to be working very well for the problem at hand, and by keeping the ensemble weight constant for all ensemble members over all times, this filter doesn't collapse in high dimension settings like other particle filters do. Just one remark, because I spoke about localization before, about localization for the implicit equal weight. The implicit equal weight computes model error times observation matrix exposed, while the ensemble Kalman filter normally has some ensemble approximation here. But since the implicit weight gets along without the approximation, he doesn't produce spurious correlations. Further on, if the Q matrix has some correlation range which is local, also the update will be local because it only acts in the area which is in the correlation range of Q, meaning there's some inbuilt localization by definition of the filter. And moreover, if the observation, the correlation radii of the different observation sites don't overlap, the updates can be done in parallel. But what we see all here depends really on the structure of the Q matrix which you choose for our model or for the setup which we run. And the setup we run here is a little bit simplified. Is a simplified ocean model in a simplified case where we have an identical twin experiment. We don't use real data. We use a ground truth which is known to us, and where we spin up 100 sample numbers plus the synthetic truth for 3 days. where we can still, on our rectangular domain with periodic boundary conditions, where we can still see the initial conditions, which were one stream to the east, to the west and north, and a stream to the, to the west in the north and to the east in the south. But then after 3 days, we start data assimilation every 5 minutes, where we get observations of the velocities at only these 60 points, which are marked here in blue. We continue for 7 days of data assimilation, and we see that the truth gets a bit more turbulent, and after 10 days, it's rather dynamically mixed, where we now release drifters, model drifters, onto the field of the truth after 10 days, and evolve them for another 3 days without any data assimilation. Let's take another look at how complicated this example is. If we see the truth, we see some clear deviation from the initial state. But if you use a Monte Carlo experiment, we see basically the initial state is just blurred out. But every ensemble member looks quite wild. That's if we have this chaotic behavior. And we try to improve this a lot by using 120 observed variables in a model which almost has 500,000 of state variables. The first look we take onto the error field of the mean. We have the ensemble mean and compare it to the ground truth. And we do this for the implicit weight for the EnKF without this inflation parameter and with an inflation parameter set to 0.5. The first thing, implicit weight has quite smooth error fields, very low error, but the EnKF, as I introduced in the beginning, is far off in half of the domain. And especially it has quite steep rims between the positive and negative error, and also individual dots in the error fields for the momenta, suspecting that it's quite unphysical, the solution which we get here. Inflation somehow is able to fix it, because on this screen you barely see any error, while when you look on the computer you see still some low smooth error fields. After the first statistical moment, going to the second statistical moment, looking at the standard deviation. Again, for the same setup, we see that the implicit weight, especially in the momenta, has some really strange structure. Around the observation sites, we get always these B-poles. And these B-poles come from the structure of the covariance matrix. So there's definitely something remarkably going on. And the standard deviation is very high locally. While for the implicit weight, for both cases, if you look again on the screen, you see something, but it's very low. And these local updates, these local corrections seem to distribute into the domain, into the full domain by the dynamical model. To evaluate the performance a bit more in detail than only looking into some error fields and standard deviation, we look at skill scores, which quantify the quality of the data assimilation over the entire data assimilation time span. Meaning we look how good can our ensemble predict the next forecast, the next observation. And for this, we look at the CRPS, the continuous rank probability score, which basically integrates over the difference between the empirical distribution function of the ensemble and the observation. And later on, we look on the bias. If you look in the CRPS, we do it by some logarithmic scale over time, and also some logarithmic scale over the values. What we see is, first, the implicit weight starts high, converges slowly to lower value, and then goes up again and never stabilizes. The LTKF versions both go down to more or less stable level for after 1 hour, up to roughly day 5, and then the uninflated diverges again. But we also see that the inflated version moves slower towards a stable level than the uninflated version. The CRPS is constructed in such a way that contributions to the CRPS can come from a high spread or from a bias. And that's actually the reason why we take another look onto the bias to get a bit more information where the contributions come from. Same setup, logarithmic scale on in the time, but now just standard scale for the values. We again see that the implicit weight goes much slower to values around 0 than both other methods, mimicking or repeating the behavior from before. And we see that after some time, especially implicit weight and also the LTKF without inflation starts to get high bias values, while the inflated LTKF stays significantly smaller than the other two. Rank histograms, I was surprised that I have not seen any here so far. So meaning we repeat the first hour of the data simulation, experiment all over again for different setups, here for a smaller sample size to make it computation a bit easier, and record the rank of the truths in the ensemble. Then we get, okay, first let's look on the lower ones. Normally flat rank histograms understood as consistency of the sample and are desirable. And since there's little dynamic in the Y component, all of them are more or less flat. But the LTKF, the classical one, is definitely underdispersive because it has this clear U shape, meaning the truth becomes often an outlier. It's not able to capture the truth in the ensemble. While the implicit equal weight has a slightly banded shape, but both implicit weight and LTKF are not too bad in this rank histogram case. So we have had a set of measures to evaluate them so far, but let's go back to the drift trajectory case and see what these results actually mean for drift trajectories. For drift trajectories, we released the true drifter, the red one, and followed it for 2 days and also for a 3rd day. While you see here in light blue, which you don't see, sorry, the ensemble members, and dots are the positions after 2 days. And on the right, you see the kernel density estimation after 3 days. The implicit weight spreads the particles out or the drifters out over half of the domain, while the LTKF stays very close together without inflation and misses the truth, which was clear suspicion after the rank histograms. And quite impressively, the LTKF is over 0.5 stays close to the truth and captures the truth even after 3 days. This was only one drifter. Let's take another look at another drifter, which I think is quite interesting, because this drifter does a turn like after 1 day without data simulation, suddenly makes a turn quite sharp, and it starts to drift northwards. The implicit weight, thanks to its big spread, it somehow captures this, but it not really captures this turn. The LTKF doesn't capture it at all. It goes straight on. And the LTKF with inflation seems to have the same dynamic, which forces the right turn towards the north in its example represented, and does this turn as well, and stays close to the truth again. Good. So we are back to this to the drift trajectory case, and this has shown that this localization scheme, which is close to the LTKF, which 100%, just a bit more efficient, made for sparse observations, because we really had troubles. It was hours of compute time different between the classical EnKF and the bit more efficient one. Works for sparse observations. The implicit equal weight didn't degenerate. It stays somehow usable for very high dimensional problems. But one thing I would like to pronounce is that we need a lot of measures to really evaluate data assimilation methods, and not only in RMSE or one thing, because we need to look at several things that we really get an insight and better understanding of how the data assimilation methods work. And now we have seen the synthetic case, but it would of course nice to see how this worked in practice. And the localization is the main localization. It not only works for the ETKF or for the LETKF, it also works for other versions of the EnKF, which is maybe worth testing. And there is, I appreciate questions.
Much. Maybe time for 2 questions.
It's very nice and very very good to have different methods like this. The history of the Assemblage filter is that people wanted to move away from Q covariances that are arbitrary, and so with the particular filter that you have here, they enter through the back door. So
Yes.
we are back to the same problem as we were before.
Yeah.
But that was not my actually question. The next, inflation of 50%.
Yeah.
Is a lot of inflation.
Yes.
And I appreciate that here you have a perfect product. You have the truth.
Yes.
But in real case, you will need to think of model errors somehow.
Yes.
Yeah? So what's your thought on that?
First, the thought about why we have so much inflation is we assimilate very time frequent. So if you would not assimilate, or if you don't have high inflation, we saw every time step the uncertainty was reduced, and we collapsed. For real observations, I'm not sure how this will work, to be honest.
I will point to a graphic from the inflation paper that makes it optimal.
Okay. Then I know what to look at.
It's cool, but it's not very efficient. Questions?
You go.
About the localization, very nice talk.
Thanks.
And so if I understand well, so you consider it's kind of isotropic, meaning for you and with it's this the same distance for 3 different directions.
Yes.
What that means, do you consider to use kind of a anisotropic for different directions? For example, I saw the flow is going this way for you and not for we.
Yes, we considered to use kernels which are like stretched into one direction, where it's the heavier current, but actually we didn't saw much difference. Maybe we didn't stretch far enough, but it's haven't seemed that they have not big influence on the anisotropy of the kernels or of the domains which we localize. Because we also saw we have a very strong Y current that should be longer than Y, but it didn't seem to make it.
Maybe I could make some quick comments as well. First, I'd just like to say I'd really love for us to stop using Gauss-Boricon. There's plenty of other compactly supported correlation-like functions that we can use that are much easier to write. And it's not nice to speak of someone who is not here, but Pavel Starkov is one of the most accurate people I know, and even he made an error implementing it.
So, it only takes about 2 lines.
No, it's 3 lines.
Three what?
Three lines.
3 lines. 3 long lines. Okay, and
coding difficulty should not be the decision factor for Gauss-Boricon.
Maybe you should share the code.
Everything is open source. Open public.
Somebody's having problems coding it, I can send them.
Okay, it's not elegant.
Can you speak into the room? Yeah.
And then, yes, if your modified EnKF is much faster, then that would be very interesting. So you're publishing that as a method?
Yeah.
Yeah.
I know it's something between application and method development, but we're publishing it a bit more clearly written up.
And finally, maybe so they all diverged ultimately, so I'm a little bit concerned about that.
Which one, sorry?
All of your filters diverged ultimately. Maybe I'm not sure what's the reason for that entirely, since you also used a lot of inflation, but in this case, maybe you should consider also using a more basic method like 3D bar.
Okay, I never tried any variational method, so I cannot rank it how it works. But thanks.
I think that's. Oh.
I'm going to argue against 3D more. Yeah.
Okay, yeah, then.
Okay, I think it's time to move on. Thanks again for the talk. Okay, it's just a bit very low batteries.
It's low batteries. Okay. It's a bad food. Oh, I think it's okay. It's a 3. I think.
I don't know.
60%. Good enough. Yes, that's it. No, I will handle it. Thanks. Let's see.
So our next talk, our final talk is given by Xiaodong.
Yes.
No need to.
Okay. Still, thanks for the introduction. And I have to say that I didn't jump into the water yesterday, so I have no photo to show you guys. And I think I'm a little bit tired today, so I have to ask your excuse because I'm going to sit here and present. Okay, then the talk today is about, is it on or not? Sorry. Okay, it's actually not on, you're right, thank you. Yeah, the talk today is about continuous hyperparameter optimization in ensemble common filter. And then I will start from explaining why I want to investigate this optimization problem, or I'll just say it's a chop problem in short. So, and then after explaining my motivation, I'm going to present a workflow to solve the chop problem. And I'm going to use 2 numerical examples to illustrate the performance of the proposed workflow. And then finally, I'm going to summarize the whole talk and discuss some possible future research directions. So, okay, actually, as you guys have seen in this workshop and also maybe in the literature, you can see that many data estimation algorithms, not only about the ensemble-based data estimation algorithm, but maybe data estimation algorithm in general, often they have some introduced algorithmic hyperparameters in order to improve the performance of a data estimation problem. Sorry, performance of data simulation. So I think Florian gave an example about in the inflation. So that there, I mean, the way to do the inflation can actually introduce hyperparameters. And then also here I take the ensemble common filter as an example. So here on this slide, actually that's the original update formula, right? I think many of you actually are quite familiar with this. So, and then in this case, there's no hyperparameter introduced. But in reality, often we find that the performance of the original EnKF is not really satisfactory in many applications. So then to improve the performance, often 2 kinds of auxiliary techniques will be introduced. One is covariance inflation. So here I give an example. It's actually about multiplicative inflation applied to the background ensemble. And the other popular one you guys have seen it many times or heard it mentioned many times is about localization. And for localization itself, actually, there are different schools of method like model space localization, observation space localization. And for us, when we do his matching problems, we tend to use common game like common game based localization. So then when we do localization, often we have one hyperparameters. It's often called let's say localization non-scale introduced. Okay, then this, oh, it does not move. Okay, nice. Yeah, so then from this, we can see that actually there are actually many different ways that hyperparameters can be introduced to into data simulation algorithms. And then associated with these hyperparameters that can be either tailored or empirical methods designed for the choice of hyperparameters. So my question here is that, is it possible to, in a way, come out a little bit more automated workflow to select these hyperparameters? And here, I think I will just focus on the choice of continuous hyperparameters, because later I will explain why I make this choice. So then I'm going to present the proposed workflow. Actually, the whole idea here is that I'm going to treat a data simulation algorithm. It's actually a genetic data simulation algorithm as a parametric mapping. So suppose that you have a background, either is maybe I should not use the sub index here. So if when I use sub index, this means that I'm considering ensemble based method, but they can be applied to other types of method. Okay, so here I use f as a functional to represent this data simulation algorithm. Somehow is similar to what Marshall discussed in his talk yesterday. And then in associated with this data simulation algorithm, I have let's say hyperparameter vector theta here that can contain a set of different types of hyperparameters introduced to improve the performance of data simulation. And then based on this observation, then I think in order to optimize the choice in a way of these hyperparameters, first of all, we need to, of course, choose optimality criteria. So here, what I did is that I'm going to find one or multiple sets of hyperparameter theta, such that the corresponding simulated observation, this guy, can match the real observations, DO here, to kind of a good extent. So I apologize for these annotations. I mean, for many people from meteorology, you like to use Y or H or something. But really, so here H stands for this observation operator in let's say atmospheric data simulation problems or forward simulator in reservoir data simulation problem. And here, as I said, I'm going to assume that theta are some continuous hyperparameters. The main reason is that because later on, I'm going to use the gradient of the loss function with respect to theta for optimization. So if it's discrete hyperparameters, or then we could get some problem of continuity, but of course there are some smart ways to circumvent this problem, although I do not consider it here. Okay, then under this setting, then I can actually convert a chop problem into a minimum average cost problem. So in this so-called MAC problem, my objective is to find an ensemble of hyperparameters rather than a single one, okay, to minimize the average of an ensemble of cost function. And then this cost function is actually given in this kind of conventional nonlinear least squares form. So it contains two terms. The first term, essentially we call it data mismatch. It actually measures the difference between the real observations and the simulated or predicted observations. And then you see that now this term actually depends on the hyperparameter, right? And the second term is a regularization term. So normally it's introduced to either improve the numerical stability of the inversion algorithm or try to impose some desired properties in the estimated, let's say, hyperparameters. Okay, and actually you can choose instead of using this conventional L2 norm or weight Euclidean norm, you can using other norms. So that is allowed. Then it can be shown that this MAC problem can be approximately solved by this update formula. So I guess you guys worked a lot on ensemble-based method. Then maybe immediately you can recognize that actually this is something very similar to what we have in the EnKF. And in our community, normally call it iterative ensemble smoother, which was mentioned by Dean and some other speakers. So this is the update formula, okay, based on what we have. Then I think similar to the advantages of the ensemble-based method in comparison to the conventional 4D-var or variation data estimation algorithms, where when we estimate an ensemble of hyperparameters, we have some benefits in the sense that now we don't have to explicitly know the gradient of the data estimation algorithm with respect to the hyperparameters. Because if you have a look at this update formula, so everything is there, no need to compute the gradient. But as in Dean's case, if you do know the gradient, then actually you can insert that into this update formula. That's no problem at all. And then, of course, the another advantage we often say that okay is provides some means of doing uncertainty configuration. So now instead of having a single estimation of hyperparameters, actually have an ensemble estimation of hyperparameters. And okay, then since localization is actually something popular, so I have to I pay a little bit attention to the localization in the CHOP workflow. The issue here is that unlike this, lots of state variables that have physical meanings. So here for hyperparameters, sometimes it might not have actually clearly defined physical locations. So if you want to apply the conventional distance-based localization, sometimes could be challenging. So then to circumvent this problem, actually in this work, I used something called correlation-based adaptive localization, which I work on in one of the recent papers. I'm not going to elaborate the details here. If you're interested, you can have a look at this paper. Okay, then I'm going to use two numerical examples to illustrate the performance of the proposed CHOP workflow. And actually in this talk, I focus on ensemble common filter. So, okay, then at the beginning, I take this classic test bed. It's actually in this 40-dimensional RANS 96 model. And the data assimilation algorithm is the stochastic EnKF with perturbed observations. So under this setting here, that's the plain EnKF algorithm without any modification, no hyperparameters here. But as I mentioned before, in order to improve the performance of this EnKF, often we will introduce two auxiliary techniques. Here is covariance inflation, one is equivalence inflation. And then here I chose this multi-predictive covariance inflation applied to the background ensemble member. And then this leads to one hyperparameter called, let's say, delta here. So there we are going to estimate this one. And then the second auxiliary technique is the distance-based common gain localization. And then in doing so, I will have another hyperparameter called the localization length scale. I'm going to skip the details of how I construct this localization matrix based on a given lambda. Okay. Then, so if we have a look at this modified algorithm, now I explicitly include these hyperparameters into the update formula. Then here you can see that these hyperparameters, delta and lambda, actually they will appear in a few places in this modified EnKF algorithm, right? And here I'm going to compare the performance of, okay, actually to in a way to show the performance of the CHOP workflow through two sets of experiments. So in the first setting, I'm going to use the green search method to tune these values of delta and lambda in such a way that the resulting Lumin square of the estimated state variables is closest to the true state variables. So under this optimality criteria, actually we are cheating a little bit because here we assume that we know the knowledge of the two state variables, but in reality, actually we know nothing. And I just include this setting as a reference case. And on the other hand, I'm going to apply the CHOP workflow to estimate an ensemble of data and the lambda values. And then we are going to compare the Lumen squares. And I also want to comment that in this case, this criteria, I mean, the criteria used in the CHOP workflow is realistic because all it needs to know is actually the data mismatch. So this means that everything is in the observation space, and then we know that. Okay. So here I show some results, part of the results that I obtained by these by using the green search method. Actually here I consider 4 different observation scenarios. So here this figure corresponds to the results that I observe all the available 40 state variables. And this figure to the results that only half of the state variables are observed. And here the third and the fourth corresponds to the scenarios that only 1/4 and only 1/8 of the state variables are observed. So then we can see that through this green search method, if we assume that we observe all the state variables, everything works quite nice, and we get a very good Lumen square. However, if reduce the number of observations, then the performance of the stochastic EnKF starts to degrade. And in some cases, actually, we will see filter divergence, which corresponds to the white color in these figures. And then actually, I want to say that using this CHOP workflow, no filter divergence happened. Everything works quite fine. It's very stable. And here I use the table to list the results in terms of Lumen square in these 2 sets of experiments. So in this column, actually I list the best possible results obtained by the green search method, which assumes that we know actually the true state variables. By the way, this average is actually, first, the time window is like a 5,000 integration time steps, and each time step corresponds to 0.05 unitless thing. And then I run this experiment, and repeat the experiment 20 times. So this is an average of the time average Lumen spiral, okay? And here I show this best Lumen spiral in terms of the mean value plus minus standard deviation. And here in this column, I listed corresponding the best combination of data and the lambda. So if we come, okay, and then these 4 columns corresponds to these 4 different observation scenarios. I have more results, but I just skip here for the sake of timing. Okay, if we compare the performance of the green search method and the CHOP workflow, then we can see that in these 4 different scenarios, actually, of course, the CHOP workflow, I mean, its performance is worse than this green search method. But the point here is that it doesn't not need to know these true state variables. But still, we can see that the Lumen square, the average Lumen square that I can obtain here is somehow close to these best possible results obtained by the green search method. So that, I think that's the main message here. And then in the second experiment, I increased the dimension of the Lorentz 96 model from 40 dimension to 1000. So the main purpose here is to show that this CHOP workflow can be applied to estimate a large set of hyperparameters rather than single parameter. So I'm going to explain that more. So here, again, this is the plain EnKF update formula without any hyperparameters. And then here I'm going to consider 2 modified algorithms with auxiliary techniques introduced. And then the first modified algorithm is actually the same as the previous modified algorithm in the first numerical example. In this case, I will have a single inflation factor data here plus the localization length scale. So in total, I have only 2 hyperparameters. And then this up formula, in a way, contains these 2 hyperparameters, right? And in the second modified update algorithm. Now, instead of using a single inflation factor, actually I introduced 1,000 inflation factors. So this means that for each state variable, I have a separate associated inflation factor. So here, this circle represents a show product. So it's kind of show product. And then, so in this case, I have 1,000 inflation factors estimate plus 1 localization length scale. So in total, I will have so 1,001 hyperparameters. It's actually this dimension is even higher than dimensional, little bit higher than dimension of state variables. And then I have 3 sets of experiments. So in the first set, I'm going to use this stochastic EnKF, but I used the green search method to find the best possible combination of a single inflation factor delta and a lambda. For this particular case, because we have so many hyperparameters, basically it's impossible to apply this green search method. Okay, so that's the message here. And then in the middle, in the middle, the setting corresponds to the first modified EnKF update formula. It contains only 2 hyperparameters. And I'm going to apply the CHOP workflow to estimate the values of hyperparameters. And in the third experiment, I'm going to, as I said before, I'm going to estimate an ensemble of 1,001 hyperparameters. I'm making this problem a little bit harder on purpose. And then let's see the results. What are the results I can get here? By the way, I want to mention that through this green search method, when we increase the dimension to 1,000, then filter diversions was also spotted. It's even more challenging than the 40-dimensional case. And then in this table, I summarized the results in these 3 experiments. So here I present the results. This column corresponds to results obtained by the green search method. And here is actually the best possible combination of delta and the lambda. And then in the middle column is the results corresponds to the CHOP workflow applied to this, let's say, the single inflation factor scenario. And in the last column is the CHOP workflow applied to the multiple inflation factor scenario. And of course, I mean, we can see that the green search method still does better than the CHOP workflows. As I said before, actually, then we are kind of, it's actually based on a different optimality criteria and the different degrees of knowledge available. If we just compare the CHOP workflow with a single inflation factor and a multiple inflation factor, then we can clearly see that by introducing more inflation factors into this update algorithm, actually we can substantially reduce the Lumen square errors. So then this is the main message here. So then to summarize, I think I don't want to make you guys think that this CHOP workflow is panacea to any problem. I mean, so here, first I will explain what the CHOP workflow can be used for. So it can be used to estimate continuous hyperparameters for a chosen data simulation algorithm and a chosen auxiliary technique. And the second message here is that it can be used to handle a large amount of hyperparameters. So now I think a hyperparameter estimation is not actually a particularly difficult problem under this CHOP workflow. But what the CHOP workflow cannot be done is that, cannot be used for is that, of course, it cannot be used to design new data simulation algorithms. And it cannot be used to design new auxiliary techniques. It's just what it can do is that based on the chosen data simulation algorithm and the chosen auxiliary technique, it will give you a kind of optimized choice of hyperparameters. But of course, with the aid of the CHOP workflow, I think people can start to think of more sophisticated data simulation algorithms, because actually you can introduce lots of hyperparameters. Then we use, then we can, right, previously. Okay, so that's the main message. And myself, actually, I work a lot on reservoir data simulation, but it's a bit strange that I present results in terms of Lorenzo 96 model. So in the future, I think I will be interested in applying this CHOP workflow to modify the iterative ensemble smoothers, because as I can see so far, I can introduce lots of hyperparameters into the data simulation algorithms. And of a particular interest here is that I think I plan to use it to estimate length scales in correlation-based adaptive localization schemes. So then that's some future possible topics. But I do think it might open more kind of possible applications. Yeah. Okay. So that. Oh, sorry. I need to thank the financial support from the Research Council of Norway and the industry partners. Yes. Thank you.
For the rest presentation. Yeah. Is this feasible in the context of a realistic big 3D parallel model? I mean, I guess that at every iteration, you have to run the whole assimilation game in the whole time span, right?
Yeah, that's a very good point. And I didn't mention that. Actually, you don't have, it only happens within a single data assimilation cycle. You see what I mean? It's actually only about this update formula. It doesn't involve the forecast step. So like if I go back to this update formula here, okay, this is BO, right? If you are thinking about the ensemble common filter, then I say this is the data as a time step 10. And now I do it iteratively. Only at this particular time step, I'm trying to update the estimation of these hyperparameters. Then does not involve this numerical, let's say numerical weather forecast model. It only happens as the data assimilation step. So of course, I mean, compared to the EnKF, it's more expensive because it does more iterations. But if it's not really so expensive for you to run this observation operator, you know, lots of people just use an identity, like H is identity or G is identity. It's not really so expensive to run. Here, F is the data assimilation algorithm. What you need is just run the data assimilation algorithm like an iterative ensemble common filter. Many steps. Now instead of actually estimating the state variables, you can say that I convert the state estimation problem into a parameter estimation problem.
I see that in that case, you have to have some kind of prior on.
Yeah, okay, yeah, that's fair. I think I just, I forgot detail, either it's a random Gaussian distribution or uniform distribution. I think because the hyperparameters, you might have some prior knowledge, which one will be good, which one will not be good, and there may be some range of that. Yeah.
Thank you.
So if I remember correctly, in Lawrence 96, normally we run experiments where the RMSE is around between 0.2 and 0.8.
Yeah, okay, yeah.
3 is like a crazy value compared to that.
It's I think in a way it depends on which type of algorithm you chose. And the experiment settings, like how frequent you observe the observations. So here I observe observations every 4 time steps. If you say I observe every time step, the normal square will definitely much lower. And if you assume I observe everything, will be much better. And if you use local analysis or local EnKF, the results will be better. But I'm not that's what I said actually. First, you need to choose your data assimilation algorithm, okay? But then if you have fixed data assimilation algorithm, then the chop workflow can estimate the hyperparameters for you. But you are going to compare stochastic EnKF and local EnKF. Maybe your comment could be true.
But you're using relatively sophisticated methods, and they should be tested in a scenario where they're supposed to be used. And this scenario, I'm guessing 3 bar would beat them easily.
3 bar will beat it easily.
Yes, because your prior will have barely any information in that piece.
I don't think, well, it's difficult for me to comment because when you say beat it easily, then it could be lots of different configurations. I'm not sure which one you have thought about.
Oh, there's 2.
Yeah.
Can you go to the cost function?
Yes.
Problem?
here, actually. Yeah, yeah.
So here the first term is mismatch to observation. Basically, you are thinking if you have better tuned the hyperparameter, you'll have a better fit to the observation.
Yeah.
I think my point is that's always the best penalizing term. Basically, if you think about inflation, the best inflation values we want is that gives you the best innovation statistic, which is the second order. So you want the best fit of O minus B statistics, right?
Yeah, yeah. I think that's something actually you can either you can change it or you can add it, because the cost function here, I mean, of course, you can change your cost function. You don't like a data misfit, let's say, or this nonlinear least squares cost function. You want maybe other types of measures of distance. But you can insert here. I actually have a separate paper. It's regarding how to other type of the cost function. Like here, I mentioned that typically people can use this L2 norm. You can then what if you change this to L1 norm, and here you can also change to L1 norm, right? This is also L2 norm or weighted L2 norm. I think I have a paper I can send to you. It's about explaining if you had other norms in general, how can you derive this update formula that is still very similar to the ensemble common filter. But yeah, if you want to change the cost function, then definitely you will change the update formula in the next slide. But I think the idea is still valid. You can, it's just like your preference is different. Yeah.
Thank you very much.
So there's already a lot of literature on the optimal tuning of inflation.
Yeah.
But one thing that is I find interesting here is that localization and inflation are not independent. If
yeah,
you
that could
increase localization, then you also want to increase the inflation.
That could be. Yes.
Do you have, say, visual evidence of that? That there's an ambiguity in the results?
Yeah, if you have a look at here, I think this might somehow. Actually, I do observe that they are kind of. Yeah, they are kind of have some influence on each other. Actually, if you look at this update formula, I say go back to the first update formula. You see here, if suppose that we have an update formula, right? No matter what, and then now if this sigma is slightly deviate from the optimal value, then of course the lambda should also deviate from the optimal value somehow. If you want to make the update in general still match the data well, that's how it is. I think yeah, you're right. Yeah.
Thank you for a nice talk. So I saw you at almost end. You use different inflation or delta over there for different variables, right?
Yeah.
But you consider you also use logarithm lengths for different variables as well.
Yeah, you can actually. So as I said, I mean, you don't have to restrict these hyperparameters to the inflation factor or localization length scale. Like if we link this talk to what the Matthew presented yesterday, there he said, okay, I want to treat this common gain as a constant. You can actually apply this workflow to estimate the common gain as well. So it's just up to you to choose. That's what I said. I mean, this chop workflow cannot tell you which is the best possible auxiliary technique. It means that you want to introduce what is the best way to introduce the hyperparameters. It's just that if you have chosen these particular hyperparameters, then it tells you something how to update these hyperparameters based on the observations. Yeah.
Thanks.
I think we're running out of questions, and very nice discussion so far. And I hope you guys get further discussion chance on Slack. Yeah.
Yes.
And let's thank the speakers all.
Yes. Thank you.
Next thing on the agenda is like Laurent is going to give us a closing remark.
Yes. Slack. Okay. Slack. Yeah, I think it's on. Snack.
Okay. So there's yeah, 2-3 things that we would like to say on behalf of the organizing committee. First,
I didn't see that. Sorry, I'm
very nice to have a physical hybrid web, but also physical meeting, and it was the first in a long time. For me, it's the first time I go to a conference in years. I didn't know where my shirts were. And, so I'm really happy that you could make it and make it very interesting workshop, because we've been seeing a long stretch from methodological to applications and across all the kind of questions that I could have had 20 years ago as a PhD student about. It's only one equation, the EnKF, but there's so many questions about every single term of this equation, and there's a lot of progress done in all of that. So I'm really happy about it. And then, so I wanted to put up the picture of the group that we had yesterday, but it's on Slack. You can see it if you look in. I'd like to thank also the online participants, if they can hear me. I don't know, and it's been they've been maybe a bit neglected, and feel a bit bad about that. It's the first time we have a hybrid meeting, and it's of course it's easier to favor the on-site participants. And I'd like to say that we sort of agree in the committee that we really prefer the on-site format. Not only because we struggle with the technology, but also because it's also much nicer as an experience. So
I think they neglected us. They didn't come.
You have a good point here. Yes. So yes, then in the coming years, assuming that no travel restrictions, wars, or things would come in the way, we will favor their on-site participation, but we don't decide all of the history. Then I'd like to say a word about our dear main organizer, Xiaodong. He's been driving this meeting for 8 years with a full mastery, and we never had to worry about anything. So he's been a little of a mother for us all, and 8 years is a long time, and I appreciate that you would like to do also some research. So let us give a good round of clapping for Xiaodong. Xiaodong is not leaving us. There's no cake and champagne outside of the room, but he'll be replaced by Patrick, who would have the honor to be the frontman for this committee. And so I'd like to say thanks to Patrick for accepting this mission, and I'm really looking forward to see how many percentage of the presentations you will understand in the future meetings. Not a problem. It's good to follow that, and maybe you can have a survey on Slack about which percentage of this presentation did you understand, and people can see, count the likes and all of this media stuff. So yeah, was there any other point we should put up? No, I think that was all. So that's it's a big thank you for you all, and you will see soon a YouTube channel and a repository on the North website for all the presentations. And I hope that we can take up the points that we have not discussed completely next year, and we also accept suggestions for the invited speakers for next year. It's good to have some inspiration. Thanks, and you can clap for yourselves as well.
Robert,
Yes.
where is the next portion?
I don't know.
You haven't determined yet? It's always around where.
Yeah.
But that's in general.
Yeah. So if you also have suggestions of places that you have spotted in the region, then we also can take suggestions. We have been to a lot of the nice hotels in the city of Bergen, so progressively spread and or diffuse our choices of locations further out. The longest distance we've been from Bergen in many years of the workshop, but yeah, it's the point is to have a view on fjord and mountain to go for a hike. So it's part of the spirit of the movie. Any thoughts? Thanks a lot. Thank you.